Hello there, and welcome to Sleepy Cosmic Lens. This is a quiet corner where curiosity settles into something gentle and unhurried. Tonight, we're drifting toward a place that feels impossibly far away, yet connected to us in a way that's hard to ignore. A place tucked inside a neighboring galaxy whose light has been reaching toward Earth for more than 2 million years. Right now, picture this. The faintest smudge of light in the night sky, so subtle you might miss it, is actually a colossal spiral of hundreds of billions of stars. And at its very heart, hidden behind a veil of ancient starlight, lies a beast of immense gravity that has been quietly shaping an entire galaxy for billions of years. A giant that doesn't roar or blaze like some of its kind, but lingers silently in the dark, bending the very fabric of space without demanding attention. As you settle, wherever you are right now, perhaps sinking a little deeper into a pillow, or letting your shoulders release some of the day's weight, we're going to wander toward Andromeda's center. We'll explore the secrets of its hidden supermassive black hole, an object 100 million times heavier than our sun, yet so quiet it almost seems asleep. We'll uncover how astronomers first discovered this invisible anchor, what happens at the edge of its event horizon, and the serene dance of star clusters that orbit in its grip, and we'll consider the slow, inevitable future when Andromeda and our own Milky Way galaxy will one day collide. It's a story of patience, of cosmic scales, and of a calm so profound it might just ease your own mind into stillness. Before we ease our way deeper into this drifting story, I'd love to know something simple. Where are you listening from tonight? Maybe you're somewhere with city lights just outside your window. Or perhaps you're in a place where the sky is dim enough to almost make out Andromeda itself on a clear night. What time is it where you are? Early evening, late night, or some hour drifting between? Whatever the clock says, I'm glad you're here. If you find this quiet journey soothing, or if you enjoy letting your mind soften while science takes the scenic route, it would mean a lot if you liked the video or subscribed. Small gestures like that help this peaceful corner reach others who might enjoy it too. Now, take a slow breath. Let your thoughts settle, and let's begin this slow drift toward a galaxy next door. Because inside Andromeda, wrapped in lanes of dust and swirls of starlight, there is a gravitational giant waiting for us to explore. One that has pulled countless stars into its orbit for longer than humans have existed. A place where time moves differently. Light bends, and matter follows rules that don't match the ones we experience here on Earth. And yet, in its own way, it's not chaotic at all. It's steady, predictable, almost patient. Somewhere in the faint blur of the night sky, Andromeda leans toward us. It's the most distant object your naked eye can see, though its glow is subtle, almost hesitant. In that hazy patch lies a spiral galaxy larger than our own, filled with hundreds of billions of stars. As we look at it, we see ancient light. Every photon reaching you tonight left Andromeda long before humans made tools or drew pictures on cave walls. That alone makes it remarkable. But hidden behind that soft glow is something even more extraordinary. A supermassive black hole, millions of times heavier than our sun, sitting at the galaxy's center like a quiet anchor. Even though the word monster is often used for dramatic effect in stories like this, the one inside Andromeda doesn't behave like something violent or unruly. It's more like a massive, calm weight that influences everything around it without flaunting its power. It doesn't tear the galaxy apart. If anything, it helps hold the center steady, guiding the movement of stars in a way we can measure but not directly see. There's something almost understated about the way it interacts with its surroundings. Other galaxies have central black holes that blast out radiation so intense that you can see them across the universe. Andromeda's is the opposite. It keeps to itself, quietly sculpting its environment over millions of years. If you were floating somewhere near the center of Andromeda, you wouldn't notice the black hole at first. Space around it wouldn't look chaotic or ablaze. Things would seem almost normal until you got too close, where gravity becomes intense enough to bend the paths of stars and gas. Everything down there follows predictable arcs, steady orbits, long sweeping curves shaped by the presence of something immensely heavy. From a distance, it behaves less like a monster and more like a massive anchor dropped into the galaxy long ago, affecting everything silently. Astronomers didn't discover this giant because it announced itself. They uncovered its presence by watching the motion of stars around the core. Those movements revealed something invisible but incredibly dense sitting in the galactic center. Even though Andromeda is unimaginably far away, its stars trace out paths that give away the existence of a central mass no cluster of ordinary stars could match. Observers used careful measurements of light and movement, gathering evidence patient night after patient night until the picture became clear. At the heart of M31 sits a supermassive black hole weighing in at around 100 million solar masses. It's interesting to think about how such a massive object can remain so quiet. Many black holes of this size shine brightly because material spirals into them, heating up and producing enormous amounts of radiation. But Andromeda's central black hole doesn't feed often. Most of the time, it sits without much material falling inward. That lack of feeding makes it dim compared to other supermassive black holes. Instead of a blazing core, Andromeda glows with a steady brightness produced by the combined light of its stars. Tonight, as we settle into the journey, imagine drifting close to that core, not falling toward it, just observing from a safe distance the way astronomers do with their instruments. Light from millions of stars swirls around, forming a dense, glowing region. Some of those stars are old, ancient even by cosmic standards. They drift near the center in elongated loops, their motion revealing the gravitational pull of something extraordinary. That slow choreography is one of the main clues that led scientists to uncover the presence of the giant hiding there. If you picture a galaxy from above, you might imagine graceful spirals curling outward like arms. But the center is different. It's crowded, energetic in a steady way, full of stars moving more quickly than those in the outer regions. All of them respond to the enormous mass at the core. Everything orbits something. Even here in the Milky Way, stars circle around our own central black hole. Gravity keeps the cosmos moving in these surprisingly organized patterns. In Andromeda, the same thing happens on a larger scale, shaped by a heavier and more powerful central mass. As we describe it, it might sound like a distant place made entirely of numbers and calculations, something too abstract to feel real. Yet, the truth is far more grounded. These stars are real. Their light has traveled to us across cosmic distances. Their orbits reveal the hidden structure of their home galaxy, and the giant in their center, for all its size, behaves in a calm and predictable way. Nothing about Andromeda's core is chaotic in the way we often imagine when we hear the word black hole. The space around it is structured, steady, shaped by laws of physics that behave consistently even in such extreme environments. Many people imagine black holes as hungry, destructive objects. But the one in Andromeda isn't consuming everything nearby. Most material stays in stable orbits. It's only when something happens to drift too close, perhaps nudged by a passing cloud of gas or a nearby star, that the black hole's gravity takes over and pulls it inward. That doesn't happen often. The region around the black hole is mostly empty space. Even inside this dense galactic core, stars maintain comfortable distances from one another almost all the time. The enormous scale makes direct collisions rare. So even here, in one of the most extreme environments imaginable, things are surprisingly steady. Thinking about a place like this can be oddly restful. You would expect something so massive and powerful to behave stormily, but instead, it sits quietly in the dark. It's not that the black hole lacks influence. It shapes everything around it with its gravity, but it doesn't radiate wildly or send out beams of energy like the dramatic examples you might have seen in images or movies. Instead, it holds its position, balancing forces, maintaining structure, guiding stars without pulling them apart. As we drift through the thought of this ancient object, the mind automatically slows down a little. The immense timescales, the steady behavior, the smooth orbits, all invite a quieter kind of focus. Even the idea that its light takes millions of years to reach us gives a sense of distance that makes our daily concerns feel small in a comforting way. The universe moves slowly. It doesn't rush. Andromeda's core has been doing what it does for longer than Earth has had continents shaped the way we know them today. That sense of deep time can settle the mind, offering room to breathe. What makes Andromeda's black hole even more intriguing is its history. It wasn't always this size. Supermassive black holes grow over time, gathering material during active periods or merging with others during galactic collisions. Andromeda itself has merged with other galaxies in the distant past, and each event added a little more mass to the central black hole. Now, it rests as one of the heaviest known in our local group of galaxies, though it rarely makes its presence known through dramatic flares or bursts of energy. Instead, it keeps a quiet profile, which is unusual for something so massive. As our thoughts continue to move through this distant galactic center, imagine slowly turning your attention to the stars that orbit nearby. Many of them move in precise paths. Some follow tight loops close to the core. Others travel in longer, sweeping arcs. Observing their motion is like reading a story written in gravity. Each star tells us something about the mass that anchors it, and those details come together to reveal a picture of a heavy central object controlling the structure of the entire region. Even though this enormous black hole remains invisible to the eye, the consequences of its mass ripple through the galaxy in steady, measurable ways. Astronomers use those motions to chart out the shape of the gravitational field. They map it, they study it, they refine their measurements. Bit by bit, patient observation reveals details about the black hole's behavior, even though we'll never see the object directly. Light cannot escape a black hole, but the things it affects give away its presence clearly. Somewhere in the center of Andromeda, this giant continues its quiet existence, unchanged by the fact that we are here many light years away thinking about it. Its behavior won't shift because we're paying attention. It doesn't flare brighter or grow noisier. It simply maintains the gravity that holds the central region of its galaxy together as it has for countless ages. That slow, steady presence feels almost reassuring. Even the cosmos has places where things remain constant. So, as we ease our way from this introduction into the broader story, let your thoughts remain comfortable. You don't have to grasp every detail. You don't need to visualize every orbit or calculation. Just let the sense of a neighboring galaxy drifting in the night sky stay with you, calm and steady. The giant at its center is waiting for us to learn more about it, and there's so much more to explore about this quiet, powerful presence inside one of the most recognizable galaxies we can see from Earth. Andromeda sits beside us in the cosmos in a way that feels almost neighborly once you become familiar with its place in the sky. It isn't loudly visible, and most people go through life without ever noticing that a faint, stretched-out smudge just above the horizon on certain nights is actually another galaxy. But when you finally recognize that the pale patch is a true island of stars, something shifts in how the sky feels. The universe becomes a little larger, but also a little more connected. That dim glow holds hundreds of billions of suns, swirling gas, enormous star clusters, and a central mass that shapes the entire galaxy. It stands out as a companion to our own Milky Way, close enough to study, yet distant enough to feel unreachable. Knowing that its light left long before humans existed can create a sense of distance. But thinking of it as our nearest large galactic neighbor pulls it close again. Most of the time, when we imagine the universe, we picture things spread out so far apart that they barely interact. Yet the Milky Way and Andromeda are part of a small community called the Local Group, a neighborhood of galaxies linked by gravity. They are the two largest members, slowly approaching each other across a gulf that seems huge by earthly standards, yet modest on a cosmic scale. If you could drift above both galaxies and watch them from afar, they'd look like a pair of spirals gradually leaning toward each other, taking billions of years to complete the approach. For now, though, they remain separate, and Andromeda keeps its distance just enough that we can study it clearly without being caught inside its influence. Every time we talk about Andromeda, it helps to remember just how massive and dynamic it is. Even though it appears small to the eye, the galaxy spans far across space, more than twice the width of the Milky Way. It has bright lanes of stars that spiral outward like gentle arms, each one filled with clusters where new stars are born and old stars drift into the later stages of their lives. Those lanes trace patterns shaped by gravity and angular momentum, forming structures that take millions of years to evolve. And yet, while it's full of motion and change, the galaxy maintains an overall shape that remains familiar and steady. Inside those sweeping arms, dust clouds gather and new stars begin to shine. These clouds contain the raw material of stellar formation. Over time, gravity pulls pockets of gas together until they collapse under their own weight, igniting nuclear fusion at their centers and creating newborn stars. Many of those young stars shine with a brilliant blue light, not because they're close to us, but because they burn hotter and shorter than older, cooler stars. Their intense glow adds brightness to Andromeda's arms and makes those regions stand out in images taken by telescopes. When astronomers capture those images, what they see isn't simply a snapshot of a galaxy, but a record of billions of lives at different stages, all existing in the same vast system. In the darker spaces between the arms, there are older stars drifting quietly, their lifetimes stretching across billions of years. These stars give Andromeda much of its steady glow, the kind that can reach Earth across intergalactic space. When you see Andromeda with your own eyes, even as a faint blur, most of the light you're seeing is not from dramatic young stars, but from ancient ones that have been shining steadily since long before humans walked on Earth. They are the quiet majority, contributing to the soft brightness that makes Andromeda one of the most distant objects visible without equipment. Studying a galaxy so far away might sound challenging, but astronomers have developed many methods for gaining insight into its structure. They measure light, track motion, and study the way stars are distributed throughout the disk. Every observation helps build a clearer picture of the galaxy. They learn how fast stars are rotating around the center, how gas clouds move through the spiral arms, and how gravity shapes everything from the smallest clusters to the largest structures. It's a patient process, but each detail adds to the story of how Andromeda formed, how it changed over time, and what it's heading toward in the future. One of the most surprising things about Andromeda is just how active it has been throughout its history. It hasn't lived a quiet, isolated life. It has merged with other galaxies, pulled in small companions, and reshaped its structure after those collisions. Galaxies often grow through interactions like this, absorbing nearby systems and adding their stars to their own. Andromeda's halo, a large spherical region surrounding the main disk, contains remnants of these past mergers. Streams of stars curve around the galaxy, the leftover trails of smaller galaxies that were torn apart and incorporated into Andromeda. These stellar streams help astronomers trace the galaxy's formation history, showing where material came from and how it was added. Although it's huge and dynamic, Andromeda isn't chaotic. Its structure has settled into a balanced arrangement shaped by gravity and rotation. The spiral arms maintain their general pattern, the central bulge remains bright and dense, and the outer regions drift in wide arcs around the center. Nothing moves quickly on human timescales, yet everything is in motion. The galaxy rotates so slowly that a single full turn takes hundreds of millions of years. And by the time one rotation completes, entire species could rise and fall on Earth. Thinking about these timescales can create an unexpected sense of calm. The universe moves at its own pace, unhurried and steady, and galaxies reflect that pace in everything they do. As we continue observing Andromeda, the idea of it being a neighbor becomes even more noticeable. Its distance is large, roughly 2.5 million light-years. But in cosmic terms, it's close enough that we can study individual stars within it using powerful telescopes. That proximity gives us a level of detail we don't often get when looking at other galaxies. We can identify clusters, map out structures, and follow features that would be too faint to examine in more distant systems. This closeness also means we can compare Andromeda to the Milky Way in meaningful ways, seeing similarities in shape and composition, but also noticing differences in mass, rotation, and the activity at the core. What draws much attention is the fact that Andromeda is gradually moving toward us. It's not drifting away like many galaxies that participate in the general expansion of the universe. Instead, the gravity between our galaxies pulls them closer, reducing the distance by about 100 kilometers per second. Even though that sounds fast, the total separation is so large that the process takes billions of years. Our descendants, if humanity continues far into the future, might witness the early stages of the eventual collision. For now, though, the approach is gentle and slow, more like a gradual leaning in than a dramatic rush. The galaxy's movement toward us doesn't affect our daily lives in any direct way, but knowing it's happening adds another layer to the story of our cosmic neighborhood. Inside Andromeda, the region surrounding the center is particularly interesting. The brightness increases sharply as you move inward, not because of dramatic energy bursts or intense feeding events, but because the density of stars increases. Millions of stars crowd into the central bulge, their combined light creating a glowing region visible across space, and somewhere inside that glow lies the massive black hole we spoke about earlier, the one that anchors the galaxy and influences the motion of everything nearby. Unlike many active galactic nuclei that radiate brightly, Andromeda's central black hole rarely feeds, so the core remains calm and steady. Even though the black hole doesn't dominate the galaxy with bright emissions, the central region remains one of the most studied parts of Andromeda. Astronomers gather information by tracking the motion of stars near the core. These stars move in patterns that reveal the gravitational landscape. Their paths curve in predictable ways that match the influence of an extremely massive central object. By measuring their speed and the shape of their orbits, scientists estimate the mass of the unseen giant. These measurements help refine our understanding of how massive objects behave inside galaxies and how they affect their surroundings over time. When people first hear about galaxies moving, changing, and interacting over billions of years, it can sound unfamiliar. The time scales dwarf anything humans experience daily. But once you become accustomed to thinking in cosmic terms, something interesting happens. The galaxy begins to feel almost like a large, slow-moving system with its own rhythm. It rotates steadily, forms stars at a measured pace, gathers material from surrounding space, and carries the traces of ancient collisions in its halo. The stability of its long-term behavior gives it a sense of quiet continuity. Taking a moment to think about where Andromeda sits in the night sky can make the experience more grounded. On a clear night, far from city lights, you might find it rising above the horizon, an elongated blur that doesn't look like much until you know what you're seeing. Once identified, it becomes easier to locate again. It doesn't flicker sharply like a star. Instead, it appears soft and diffuse. That appearance comes from its enormous distance. The light from billions of stars merges into a single faint glow by the time it reaches your eyes. Knowing this makes the sight of it feel more personal. You're seeing something vast with nothing more than your eyes. The galaxy's presence in the local group also ties it closely to the Milky Way. These two large galaxies shape much of the gravitational environment around them. Smaller galaxies orbit both of them, forming a small community of systems bound together. Some of these smaller galaxies are satellites of Andromeda, circling around it the way our own satellite galaxies orbit the Milky Way. Their paths reveal additional information about the mass and gravitational influence of the larger systems. Studying these satellites helps researchers understand how galaxies grow and how material moves through the local group. Another remarkable part of Andromeda's story is how much brighter it appears in telescopes than it does to the naked eye. When high-resolution images are taken, the galaxy reveals an incredible amount of structure. Dust lanes trace dark, curving shapes across the bright disk. Star clusters appear as compact glimmers. Regions of new star formation stand out clearly. All of these details create a picture of a galaxy that is active, complex, and full of ongoing change. Observers piece together these features to understand the cycles that shape the galaxy. Each element contributes to a long-term narrative that spans billions of years. Looking closely at these features gives insight into the galaxy's past. The distribution of stars, the presence of dense clusters, and the arrangement of stellar streams all point toward a rich and dynamic history. Andromeda hasn't remained untouched. It has swallowed smaller galaxies, rearranged its own stars, and evolved into the spiral shape we see today. The evidence of those past events still lingers in the form of stretched-out trails and loosely bound clusters. These remnants serve as clues that help map the galaxy's development. While Andromeda is large and intricate, it isn't overwhelming when approached patiently. Thinking of it as a nearby companion makes it easier to connect with. It sits just beyond our galaxy, sharing the same broad cosmic environment, shaped by similar physics and following similar processes of star formation, rotation, and long-term evolution. Observing it feels almost like looking at a larger version of our own home from an external viewpoint. The similarities help us understand our own galaxy more clearly, while the differences highlight the diversity of structures the universe can form. As we keep thinking about the galaxy next door, there's something calming about the way it moves through space. Nothing about it is hurried. Stars age gracefully, clusters drift slowly, and the galaxy approaches us with a patience that only cosmic timescales can provide. Even the central black hole, enormous as it is, remains quiet. Almost everything in Andromeda happens slowly, giving the galaxy a sense of steadiness. That steadiness invites ease. You don't have to imagine complex interactions or violent events. You can simply picture a spiral galaxy existing as it has for ages, breathing in the dark, shaped by gravity and the long currents of time. When you drift your attention toward the center of Andromeda, the first thing that stands out isn't the black hole itself. Even with powerful instruments, the object remains unseen because nothing escapes it, not even light. What you notice instead is the brightness of the region surrounding it. There's a concentration of stars so dense that their combined glow creates a steady, warm brightness in the center of the galaxy. That brightness is what wraps around the silent giant, hiding it behind the collective light of countless suns. It almost seems as if the stars have formed a protective covering around something that does not radiate on its own, something that rests deep inside the glow without revealing its shape. Most of the time when people imagine a supermassive black hole, they picture something violent or chaotic, perhaps swirling beams of radiation or jets shooting across space. That picture fits some galaxies very well, especially the ones with hungry black holes drawing in large amounts of matter and creating enormous outbursts. Andromeda's central black hole behaves differently. It doesn't give off a dramatic light show. It doesn't send out jets. Instead, it stays quiet, doing little more than anchoring the region with gravity. Its presence is known not because it announces itself, but because the stars around it move in ways that signal the grip of something far heavier than anything visible. As you imagine drifting through this central region, you might think of a smooth field of light created by millions of stars whose orbits cross and layer over one another. They move at speeds shaped by the black hole's mass, but not in a way that looks chaotic. Their paths fall into stable loops, narrow ellipses, or more rounded orbits depending on their distance from the center. Each orbit is a clue. When astronomers study these motions, they find that the closer a star is to the central mass, the faster it travels. These speeds are too high to be explained by ordinary matter alone. Only a supermassive black hole could create a gravitational field strong enough to generate motion of that kind. It helps to picture this region in steps. First, there is the glow of old stars forming a dense cluster. These stars are often smaller and cooler than the bright blue ones found in the galaxy's arms. They have aged over billions of years and moved inward gradually, forming a populated region that offers a natural marker of the galaxy's center. Then, inside that glowing cluster, the gravitational pull increases sharply. There is nothing visible there, yet the motions of nearby stars bend inward. Their paths curve in ways only a very massive object could explain. That unseen mass sitting deep inside the glow is Andromeda's black hole. Even though the word silent is often used casually, it truly applies here. There is no noise in space in the way we hear sound on Earth, but there are still forms of activity that can be detected through light, radio signals, or energetic emissions. None of those signs appear strongly around Andromeda's center. The black hole there barely feeds. Very little gas falls toward it. Very few stars pass close enough to be torn apart. Without those events, the region stays calm. Most of what happens nearby follows predictable patterns, and the black hole's influence remains steady and quiet. One reason Andromeda's black hole is so faint is that it has already cleared out much of the material that once surrounded it over billions of years. Any gas cloud drifting too close would have been pulled inward, heated, and eventually swallowed. After long periods without new material falling in, the region becomes relatively empty. Stars still orbit there, but the black hole doesn't gain much mass through regular feeding. That lack of activity lowers its brightness in nearly every detectable wavelength. In many ways, its silence tells astronomers more about its environment than an outburst would. Even though the core looks peaceful, the forces at play are immense. If you could observe the space just outside the event horizon, you would see matter moving at extraordinary speeds. But the region around it is so empty that little is visible. There are no large swirling disks or bright streams of gas. If matter did fall inward, there would be a brief increase in brightness as it heated, but those events occur rarely. For the most part, the black hole continues its quiet existence, influencing the galaxy on timescales measured in millions of years. Watching how Andromeda's stars behave near the center has given astronomers a great deal of insight into the relationship between galaxies and black holes. Measurements show a strong connection between the mass of the central black hole and the properties of the galaxy's bulge. Larger bulges tend to host larger black holes. This relationship appears in many galaxies across the universe, suggesting that the growth of a galaxy and the growth of its central black hole may be linked. Andromeda fits that pattern well. Its bulge is large, bright, and dense, and at its core sits a massive black hole that matches this size. Another interesting element of this region is the double nucleus. When astronomers look closely at Andromeda's center, they see not one bright peak, but two. The brighter of the two is slightly offset from the actual black hole. This unusual structure results from a cluster of stars orbiting in such a way that they appear to form 2 points of brightness when viewed from Earth. The stars close to the black hole move faster, creating a compact region. The more distant group appears as a second bright spot. Even though this structure seems complex, it follows stable orbital paths shaped by gravity. Thinking about these arrangements makes the central region feel less like a chaotic environment and more like a crowded but organized system. Each star moves according to the black hole's influence, the mass of the surrounding cluster, and its own momentum. These combined effects create a balance that holds the region together. Nothing rushes, nothing leaps unpredictably. Everything follows steady paths, sometimes taking thousands of years for a single orbit, sometimes taking millions. In a sense, the stars near the center form a kind of curtain around the black hole. Their combined light blocks any direct view of what lies inside, but their motions expose the mass hidden there. This curtain is not a physical barrier, it is simply the effect of so many stars crowded together. Their brightness gives the center its glow. If the black hole surrounded itself with a dramatic disk of glowing gas, that disk might outshine the stars. But because it is quiet, the starlight dominates. Even though the black hole is enormous, its size in space is surprisingly small compared to the region it influences. The event horizon of a 100 million solar mass black hole spans only a fraction of a light year. Meanwhile, the central cluster extends across many light years. The black hole occupies only a tiny part of that space, yet everything within thousands of light years responds to its presence. The idea that such a concentrated object can control such a wide region shows how gravity behaves on large scales. The stars near the center often follow unusual paths. Some move in tight, elongated loops. Others travel in long, stretched-out orbits that bring them close to the core and then far into the surrounding cluster. These motions help astronomers determine not only the black hole's mass, but also the distribution of stars in the central bulge. By watching how light shifts as stars move, they can estimate speed, direction, and distance. Taken together, these details reveal a system shaped by long-term gravitational interactions. Even though the black hole itself sits quietly, it has almost certainly seen active periods in the distant past. There would have been times when gas clouds spiraled inward, creating bright emissions. There may have been epochs when the black hole fed more regularly, generating radiation that would have outshone the entire galaxy. Those periods have ended for now, but traces might still exist in the form of heated gas or subtle structural changes in the central region. The calm appearance today is only one phase in a long history. Thinking about how such a massive object grows can be grounding. Supermassive black holes don't appear at their enormous sizes immediately. They start smaller, often forming from the collapse of early massive stars or dense clusters. Over time, they gain material, merge with other black holes, and gradually expand. Andromeda's central black hole reached its current mass through countless interactions across billions of years. Each event added a small amount of growth, eventually building the giant we infer today. The starlight surrounding this black hole represents the long life of the galaxy itself. These stars have formed, aged, and drifted inward over enormous spans of time. As they moved, they contributed to the central glow, creating the bright region we observe. Some stars have been near the center since the early days of the galaxy. Others arrived more recently. Their combined presence gives Andromeda its structure and hides the black hole within a stable and consistent environment. When astronomers observe this region, they gather information not just about the black hole, but about galaxy formation in general. The distribution of stars, the shape of the bulge, the double nucleus, and the orbital patterns all provide clues. Andromeda offers a chance to study these features at a distance that is close enough for meaningful detail, yet far enough for the entire structure to be viewed at once. Few galaxies give such a clear opportunity, even though the black hole doesn't produce light on its own. The stars around it continue to grow older, evolve, and eventually shed material back into the galaxy. Some of that material might drift inward, but most will remain in the central bulge, slowly getting redistributed by gravitational interactions. The entire region functions like a complex but stable system. Nothing about it happens rapidly. Each change unfolds slowly over timescales that are difficult to compare to human lifespans. Spending time imagining this silent giant helps create a sense of scale. It reminds us how large the universe is, how long cosmic processes take, and how steady many of these systems remain across unimaginable spans of time. The black hole is powerful enough to bend space itself, yet it sits quietly, wrapped in the collective glow of millions of stars. Nothing about it seeks attention. Nothing radiates loudly. It simply exists, influencing the galaxy with gravity alone. When people talk about galaxies, they often think first about the wide spiral arms or the soft glow that stretches across the sky. Those features are noticeable, and they define what we see when we look from far away. But every large spiral galaxy has something deeper at its core, something that doesn't shine or spin with visible light, yet holds the entire system together with unyielding force. In Andromeda's case, that anchor is the supermassive black hole resting quietly in the center, shaping the galaxy's motion through gravity alone. If you could remove that central mass, the structure of the galaxy would not collapse instantly, but over long stretches of time, the careful balance that holds the spiral together would gradually shift. That central object isn't the only component that defines the galaxy's structure, but it plays a crucial role in keeping the inner region stable and the orbits of stars consistent. Thinking about a supermassive black hole as an anchor can feel unusual because anchors are usually imagined as solid, visible objects. This one isn't visible at all. Nothing escapes it, and it emits almost no radiation to mark its presence. Yet it influences everything around it. Stars near the center of Andromeda don't move randomly. They follow paths determined by the combined mass of the bulge, the gas, and the black hole. But the black hole's gravity dominates the smallest inner region. Without that anchor, those stars wouldn't have the same compact distribution. Their motions would be different, and the bulge would not maintain its familiar shape. Anchoring a spiral galaxy doesn't mean pulling on every star individually. Gravity weakens with distance. Stars far from the center respond more strongly to the mass of the galaxy's dark matter halo and the distribution of stars throughout the disk. Even so, the central black hole shapes the galaxy's character. The region closest to the center rotates more quickly and more tightly than it otherwise would. Those motions ripple outward in subtle ways, creating a stable inner structure that allows the spiral arms to persist. While the arms themselves aren't held together by the black hole directly, the inner gravitational environment helps define how the galaxy rotates. If you zoomed into Andromeda's central region with the most powerful instruments, you'd see the paths taken by stars moving in elongated loops, some extremely fast. Their speeds reveal the strength of the gravitational pull they experience. Astronomers measure these speeds through the Doppler effect, observing shifts in light as stars move toward or away from us. Those measurements give direct information about the mass in the center. That's how the presence of the black hole was confirmed. There was no need to see the black hole itself. The stars acted as markers circling something they could not avoid. The idea that something invisible could hold a galaxy together first appeared when astronomers studied the motions of stars in the Milky Way. They realized that only an extremely massive but unseen object could explain the speed of stars near the center. Andromeda offered a much clearer view of this process because its central region is easier to observe from Earth's perspective. As telescopes improved, the evidence grew stronger. Every new measurement confirmed that the central object in Andromeda is enormous, concentrated, and dense enough to qualify as a supermassive black hole. Even though the black hole does not shine, the stars around it create a brilliant display of motion and light. Their presence forms a kind of map of the gravitational field, showing where space bends most sharply. The black hole sits at the exact point where that bending becomes strongest. Nothing special marks the location visually. It would look like a dark spot if not for the surrounding stars, but in practice, it blends seamlessly into the central glow. Only detailed measurements reveal where the true center lies. The stars make loops, and those loops converge on a region that cannot be explained by normal matter. When astronomers describe this black hole as anchoring the galaxy, they aren't suggesting it holds everything in place single-handedly. Instead, they mean that its presence contributes to the stability of the entire system. Galaxies need organized rotation to maintain their shape. Without that rotation, material would collapse inward or drift outward. The inner region plays a key role in setting the rotation curve, the pattern that describes how fast stars move at different distances from the center. The mass at the core defines the beginning of that curve. Although dark matter dominates the outer parts of the galaxy, the central bulge and black hole control the inner portion. That balance creates the conditions for the spiral arms to form and maintain their structure. If you focus on the stars closest to the center, their behavior becomes especially informative. These stars move incredibly fast, sometimes reaching speeds of hundreds of kilometers per second. Their orbits are tight, looping, and stable. If they come too close to the black hole, they risk being torn apart. But most of them travel in safe paths that remain constant over many cycles. Their stability is incredible considering the gravitational forces involved. The only reason these stable orbits exist is because the black hole creates a smooth gravitational environment, powerful but not chaotic. It's as though the black hole provides the central weight that keeps everything centered. This central weight has another interesting effect. It helps define the density profile of the stars near the core. When material drifts inward over long periods, the black hole influences how that material settles. Stars migrate inwards slowly through gravitational encounters, interactions with other stars, and the natural evolution of the galaxy. Over billions of years, those processes build up a dense environment around the black hole. The density increases gradually as stars accumulate in the region. That buildup reflects the black hole's long-term impact on the galaxy's structure. Thinking about these interactions can make the black hole seem like a passive presence, but it plays an active role in shaping the galaxy's past and future. During earlier stages of Andromeda's history, the black hole likely went through periods of significant feeding. When galaxies merge, gas clouds can be pushed toward the center, providing fuel for the black hole. During these periods, the black hole might have been orders of magnitude brighter than it is now. It might have produced radiation powerful enough to influence star formation in the surrounding region. Those active periods may have helped shape the bulge, enriching the gas and influencing how stars formed afterward. The silence we see today is just one phase in a long cycle. Anchoring the spiral world also relates to how the black hole interacts with the surrounding stars through long-term gravitational effects. Every time two stars pass near each other, they exchange a small amount of energy. Over billions of years, these small exchanges add up. Stars gradually spread outward or drift inward depending on their encounters. The presence of the black hole creates a center that stabilizes these interactions. Without that central mass, the stars would not converge in such a compact cluster. Instead, the region might become more diffuse, widening over time. The black hole's gravity draws the inner stars together and shapes the central bulge into the dense structure we see today. When astronomers simulate galaxy formation, they often find that galaxies with central black holes develop differently than those without one. The black hole helps regulate how material moves in the central region. It stabilizes the bulge, influences the rotation, and occasionally affects how gas cools and forms stars. Even though the black hole is small compared to the galaxy as a whole, its influence reaches far beyond its immediate surroundings. Gravity is persistent. Once established, the black hole continues shaping the galaxy without needing to consume material or produce dramatic events. Considering the black hole in this way helps shift the focus from its more dramatic potential behaviors to its steady, grounding role. Most depictions of black holes emphasize destruction and consumption, but the one in Andromeda mostly exists as a predictable gravitational presence. It doesn't erupt or flare frequently. It doesn't tear apart the structure around it. Instead, it functions as a natural keystone, a mass so large that the galaxy organizes itself around it. That organization gives the spiral its long-term stability. Even if you move far away from the center, the black hole still plays a part in defining the galaxy's overall behavior. Spiral galaxies rotate in characteristic ways. Their rotation curves show how fast stars move depending on their distance from the center. While the outer regions are dominated by dark matter, the inner curve is shaped by the central bulge and black hole. That means the anchor at the center contributes to the pattern of rotation that governs how the arms form and persist. Without that central mass, the rotation curve would shift and the spiral structure might develop differently. Thinking about the galaxy as a whole, it becomes clear that the black hole is not the sole architect but part of a balanced system. The stars, gas, and dark matter all contribute to the galaxy's shape, but the black hole remains the single most concentrated mass in the entire system. That concentration gives it a unique role. It sits at the center of gravity, the point around which everything else moves. Even though its immediate influence diminishes with distance, the overall structure of the galaxy would not be the same without it. Astronomers continue to study Andromeda's center to understand these relationships better. Improved instruments allow them to measure star motions with increasing precision. They track how stars accelerate as they approach the core and how they slow as they move outward. These measurements refine the mass estimate of the central black hole, giving more accurate values over time. They also provide insight into how black holes form and evolve. Every new observation adds to the growing body of knowledge about the connection between galaxies and their central giants. As the story of Andromeda continues, it becomes easier to appreciate the black hole not as a destructive force, but as a stabilizing one. It has shaped the galaxy for billions of years, influencing everything from star orbits to the structure of the bulge. It stands at the center of a spiral world, providing the gravitational foundation that allows the galaxy to exist in its current form. This anchor does not shine, does not move visibly, and does not announce its presence, yet it remains essential. Long before anyone could imagine the scale of a supermassive black hole, astronomers studying Andromeda noticed something unusual in its center. They didn't see anything dramatic. There was no glowing disk, no outburst, no jet of light. Instead, there was a tight cluster of stars behaving in ways that raised questions. Their motions didn't match what observers expected, and the speeds at which they drifted around the core didn't fit with the mass that seemed to be present. Something unseen was shaping their paths. It wasn't obvious at first. The hint arrived through small details, the kind that can be overlooked unless someone is paying attention to patterns that don't quite line up. In the early days of studying galaxies, astronomers mostly focused on visible light. They looked at the brightness of stars, the shapes of galaxies, and the structures that could be photographed with the telescopes of the time. Andromeda's core seemed bright but not extraordinary. It looked like a dense but normal bulge of older stars. Observers knew it was crowded, and they could tell the stars near the center were moving, but the details of those motions weren't clear yet. The technology didn't exist to measure individual stellar speeds with the precision needed to identify the presence of a supermassive object. As telescopes improved, researchers gained the ability to measure light more precisely. That meant they could observe tiny shifts in the wavelengths produced by stars moving toward or away from Earth. These shifts, called Doppler shifts, offered a way to estimate stellar speeds. When astronomers applied these methods to Andromeda, they found something surprising. The stars near the center were traveling at velocities far higher than expected. Those speeds couldn't be explained by the visible mass alone. Something else had to be there. At first, some astronomers suspected there might be an unusually dense cluster of stars hidden behind the brighter ones. That explanation seemed reasonable. After all, galaxies contain many types of stellar populations, and some clusters can be extremely dense. But when they calculated how much mass would be needed to produce the observed speeds, the numbers didn't fit. Even the densest cluster imaginable couldn't account for the gravitational pull necessary to keep those stars in stable orbits. Another possibility was a concentration of dark matter. Researchers knew dark matter influenced the motion of stars on large scales. Perhaps a concentrated core of dark matter lay at the center. But dark matter doesn't behave like normal matter. It usually spreads out over large regions rather than forming compact clumps. Observations of other galaxies suggested that dark matter halos do not gather densely enough in their centers to explain these motions. The idea didn't hold. The only remaining explanation was an object so massive and compact that nothing else in physics could describe it. One of the earliest key pieces of evidence came from studies of the central light profile of Andromeda. Astronomers used detailed imaging to map the brightness of the core. When they plotted the brightness against distance from the center, they found a sharp rise near the very middle. The stars crowded together tightly, and the pattern of light suggested a gravitational influence stronger than what could be produced by the stars themselves. That rise hinted at a heavy object sitting in the exact place where the orbits converged. Still, the evidence wasn't conclusive yet. Later in the 20th century, when more advanced instruments became available, astronomers gained the ability to detect the motions of stars very close to the center. They discovered that the stars followed patterns consistent with orbiting a single massive point. Their paths matched calculations for motion around something incredibly dense. Researchers compared the data with theoretical models, and each comparison pointed toward the same conclusion. A supermassive black hole was the simplest explanation for the observed behavior. No other known object could produce the necessary gravitational pull in such a compact space. At the same time, spectrographs became more sensitive. These devices separate light into its component wavelengths, allowing astronomers to study how light changes as stars move. The central region of Andromeda produced signals indicating rapid rotational motion. The light coming from the region was shifted in two distinct directions, reflecting the rotation of stars moving both toward and away from Earth. This rotation wasn't slow, it was intense. The speeds indicated a central mass far larger than any cluster. One important moment arrived when astronomers used the Hubble Space Telescope to gather detailed imagery of Andromeda's center. Hubble's resolution allowed researchers to see the double nucleus, a structure that puzzled them at first but soon became a significant part of understanding the central mass. The double nucleus consisted of two bright concentrations of stars close to one another. Initially, some suspected there might be two separate massive objects, but further study showed that the two bright spots were formed by a single ring of stars orbiting a central mass. Their orbits made them appear as two bright peaks when viewed from Earth. This ring of stars wasn't a simple structure. The stars in the ring moved in elongated orbits that were shaped by the black hole. If the black hole had not been there, those stars wouldn't have followed the same paths. The ring acted almost like a fingerprint, marking the presence of the heavy object at its center. By studying the ring's shape and motion, astronomers refined their mass estimates. The results were consistent with a black hole weighing roughly 100 million times more than the Sun. Another clue came from infrared observations. The central region is crowded and dust-filled, so visible light can only reveal part of what is happening. Infrared light penetrates the dust more easily, allowing astronomers to observe stars hidden from view. When infrared data became available, it confirmed that stars in the central region moved too quickly to be bound by anything other than a supermassive black hole. Their speeds were simply too high. Without the stabilizing gravitational force of the black hole, the stars would fly apart or disperse. Radio observations also played a role. Although Andromeda's black hole is unusually quiet, it emits a faint radio signal. This emission isn't strong like the jets from more active black holes, but it provides yet another indication that something compact and energetic lies at the center. The radio signature matches what would be expected from a black hole accreting small amounts of material. Even though the feeding rate is low, the signal is detectable with sensitive instruments. These observations, taken together, gradually built a clear picture. There was no single moment when astronomers suddenly announced the discovery. Instead, the understanding developed step by step. Each new piece of data supported the idea of a massive, invisible object at the heart of the galaxy. Over time, skepticism faded as the evidence grew overwhelming. Andromeda's central black hole became accepted as a fundamental part of the galaxy's structure. One of the most important ways astronomers confirmed the presence of the black hole was through velocity dispersion measurements. Velocity dispersion describes how the speeds of stars vary in a crowded region. In the central bulge, stars don't all move at the same speed. They have a spread of velocities, and that spread depends on the gravitational field. When astronomers measured the velocity dispersion near Andromeda's core, they found values far higher than could be explained without a massive central object. The dispersion increased sharply as they approached the center, pointing directly to the black hole's influence. Even without seeing the black hole, astronomers developed a deeper sense of its presence by comparing Andromeda with other galaxies. Many galaxies show signs of central black holes through similar patterns of motion. When researchers plotted black hole mass against the properties of the surrounding bulge, a consistent relationship emerged. Andromeda fit neatly into this relationship. Everything about its central region matched what would be expected from a galaxy containing a massive black hole. It wasn't an outlier or an exception. Instead, it stood as a clear example of a common galactic structure. It's also worth noting that sometimes discoveries happen because researchers look closely at something familiar and notice details others overlooked. Andromeda has been known for centuries. People studied it with telescopes long before anyone understood what galaxies were. Yet, the hidden mass at its center remained unnoticed until the right tools and methods became available. Once those tools arrived, the puzzle pieces began to align. The invisible colossus was always there, but the evidence had to accumulate slowly before anyone could recognize what it truly was. During the process of uncovering the black hole, astronomers refined their understanding of how galaxies evolve. The presence of a central black hole has implications for the formation of the bulge, the distribution of stars, and the long-term dynamics of the system. The quiet behavior of Andromeda's black hole today does not erase its influence in the past. It likely played a major role during earlier stages of the galaxy's development, shaping the environment in ways that still affect the galaxy now. Traces of those earlier interactions remain embedded in the structure. As the evidence for the black hole grew stronger, astronomers began comparing different models to better understand how the central mass interacts with the rest of the galaxy. These models simulate the gravitational field, stellar motions, and long-term evolution of the region. When the models include a supermassive black hole at the center, they reproduce the observed behavior. When the black hole is removed from the model, the match disappears. This comparison offers an elegant demonstration of the black hole's importance. It isn't just an optional feature. It is a necessary component of the system. Thinking about the discovery process makes the black hole feel even more real. It wasn't found through a dramatic flash or a single experiment. Instead, it revealed itself through patterns, motions, and slight shifts in starlight. Every one of those pieces came from patient observation. Nothing about the process was rushed. Light from Andromeda took millions of years to reach Earth, and astronomers took decades to interpret what it meant. That extended timeline adds to the feeling of calm that surrounds this entire topic. The universe doesn't hurry. The discoveries reflect that same pace. When astronomers turn their attention toward the tight cluster of stars near Andromeda's center, they weren't expecting those stars to reveal anything extraordinary. At first glance, they looked like any other dense stellar region, a bright knot formed by countless older stars packed into a compact volume. Nothing about them hinted at something unusual lurking behind their glow. Yet, as measurements improved and astronomers began to track their motions carefully, the behavior of these stars began to tell a story that nothing else in the galaxy could explain. Their swirling paths, their unexpectedly high speeds, and their tightly bound orbits became the very clues that betrayed the presence of the enormous black hole hiding in the dark. The journey to understanding these stellar motions started with careful observation. Each star in the central cluster emits light that can be broken apart into its component wavelengths. When a star moves toward Earth, those wavelengths shift slightly toward the blue end of the spectrum. When it moves away, they drift toward the red. These shifts are tiny, yet they hold valuable information about how fast the star is traveling. Early measurements were rough, but they offered the first suggestion that something curious was happening near Andromeda's core. The stars weren't drifting lazily the way they might in a quieter region. They were racing. As technology advanced, astronomers collected more precise data. They used high-resolution spectrographs attached to large telescopes, instruments capable of detecting incredibly small changes in light. When they aimed these tools at Andromeda's center, the numbers they retrieved were startling. Stars close to the core were moving at speeds far greater than anything expected from a typical cluster. These weren't slight deviations. The difference was dramatic enough that astronomers immediately knew the visible mass couldn't account for such rapid motion. Something invisible was exerting a gravitational force strong enough to fling stars around at extraordinary velocities. Visualizing these motions helps make sense of the data. Imagine standing at a distance and looking down at the center of the galaxy. In your view, the stars near the inner region would appear to move faster the closer they got to the core. Farther out, the stars would still be moving, but at more moderate speeds. This gradient in speed is a direct response to the gravitational pull of the mass at the center. In a system without a massive central object, the pattern would look different. The fact that the speeds increased so sharply near the core pointed to an extremely dense, compact mass. Some stars traveled in nearly circular orbits, following smooth loops around the center. Others took elongated paths, stretching in long sweeps before curving sharply as they neared the central mass. These ellipses were key to understanding what lay inside. When a star follows a long, stretched-out orbit, its speed increases dramatically near the closest approach point. The amount of acceleration it experiences depends on the gravitational force acting on it. When astronomers calculated the force required to produce the observed acceleration, the results were unmistakable. Only a supermassive black hole could provide that kind of gravitational strength in such a small region. The double nuclear structure of Andromeda made these measurements even more interesting. One cluster appeared slightly offset from the center, while the other sat right where the gravitational influence was strongest. Stars in the offset cluster moved in patterns consistent with a ring-shaped orbital structure. Their individual motions still responded to the central mass, but collectively they formed an elongated, lopsided brightness pattern. This arrangement puzzled researchers initially, but simulations showed that a central black hole could stabilize such a structure. The stars were essentially frozen into a particular distribution due to the gravitational environment created by the black hole. Continuing to examine these motions revealed even more complexity. Some stars traveled so quickly near the center that their speeds rivaled the fastest-moving stars in the Milky Way's central region. In the Milky Way, stars near the central black hole have been observed whipping around the core at extreme speeds. Andromeda's stars behaved in a similar fashion, though the overall structure differs due to the galaxy's larger mass and different history. Their high velocities remain one of the clearest indicators of the central black hole's presence. Without that mass, those stars could not remain bound to the core. They would fly away into the galaxy or disperse into the surrounding bulge. When researchers tracked the motions over long periods, they found that the behavior was stable. The stars didn't drift out of their orbits or slow dramatically. They continued their loops consistently year after year. These steady patterns pointed to a long-lived equilibrium shaped by the black hole. If the center contained a cluster of normal stars instead, the gravitational field would be different. A cluster made of many stars would not stay compact over long timescales. It would gradually spread out or dissipate. Only a single massive object could maintain such stability. Another important clue came from velocity dispersion measurements. When stars move randomly within a cluster, their speeds vary, and the spread of those speeds reflects the gravitational environment. In Andromeda's core, the velocity dispersion increased sharply close to the center, far beyond what could be produced by visible stars alone. The rise in velocity dispersion matched theoretical predictions for motion around a supermassive black hole. This agreement strengthened the case that astronomers were observing the gravitational footprint of something enormous and unseen. Infrared observations helped refine the picture. Dust in the central region blocks some of the visible light, making it difficult to track stars near the core. Infrared wavelengths, however, pass through the dust more easily. When astronomers used infrared telescopes to observe Andromeda's center, they detected stars even closer to the core, stars previously hidden in visible light. These stars exhibited the same high-speed motions, further confirming the presence of the black hole. Radio data added yet another piece. While Andromeda's black hole is mostly inactive, it produces faint radio emissions. These emissions come from small amounts of material falling toward the event horizon. The radio signal is weak because the feeding rate is low, but it still demonstrates that a compact, energetic object exists at the center. Alone, the signal wouldn't be enough to identify a black hole, but combined with the stellar motions, it fits perfectly into the overall picture. If you were to imagine floating near the core and looking at the stars swirling around the black hole, the scene would be deceptively calm from a distance. The density of stars would increase dramatically as you approach the center, but nothing would appear chaotic. There would be no flashes or jets. Instead, you would see a region filled with steady motion. The stars would trace graceful paths, each following a route shaped by gravity. Their swirling pattern would look organized, almost orderly, despite the incredible forces involved. Yet, if you could observe these stars up close, their speeds would be astonishing. Some would move hundreds of kilometers per second, faster when near the closest part of their orbit. Their paths would stretch in long curves before swinging sharply inward. They would not collide with each other even in such a crowded environment, because the distances between stars remain large on their scale. That balance of intense motion and wide spacing allows the region to maintain order. Scientists studying these swirling stars often use sophisticated models to simulate their behavior. These models include the gravitational influence of the black hole, the distribution of stars, and the effect of random encounters between stars. When the black hole is included, the simulations reproduce the observed motions almost exactly. Without it, the simulated stars cannot achieve the observed speeds without destabilizing the structure. This comparison helps confirm that the black hole is not just a convenient explanation, but the only viable one. Another interesting aspect of the swirling stars is the way they reveal the mass of the black hole. The faster a star moves, the stronger the gravitational pull acting on it. By measuring the speed and distance of the fastest stars, astronomers can estimate how massive the central object must be. In Andromeda, these measurements lead consistently to a mass of around 100 million suns. The precision varies depending on the methods used, but every approach confirms a mass far beyond what any cluster of normal stars could provide. Some researchers looked for alternative explanations in earlier years. They considered whether a dense cluster of exotic objects like neutron stars or stellar black holes might be responsible. These objects are heavier than normal stars and could provide more gravitational pull. However, clusters of such objects would not remain stable for long periods. They would collide, merge, or evaporate through gravitational interactions. The density required to match Andromeda's central mass is simply too extreme for any collection of smaller bodies. Only a supermassive black hole fits the constraints. Even the shape of the orbits offers clues. If the central mass were not extremely concentrated, the orbits would be wider and more diffuse. The stars would not reach such high speeds near the center. Instead, the orbits would resemble those found in ordinary clusters. But the sharp acceleration observed near the core indicates a gravitational field that only a black hole can produce. These orbital shapes act like signatures, revealing the nature of the central mass. One of the most remarkable aspects of this discovery is the calmness of the environment. Despite the extreme forces at play, nothing in the central region appears wild or chaotic. The stars do not scatter in all directions. Instead, their motion follows clear rules governed by gravity. The quiet coordination of their paths makes the hidden giant seem even more impressive. This massive object does not create destruction at every turn. It simply influences the stars through its gravity, shaping their long-term behavior. Understanding the stars that swirl around the black hole has given astronomers insight into Andromeda's past. Their motions preserve information about how the central region evolved. The distribution of orbits shows signs of previous mergers and interactions. Some stars may have been brought into the region through past galactic collisions. Others may have formed in the central bulge itself. As they settled into their new environment, their motions adjusted to the gravitational landscape. Today, these stars act as a living record of everything that has happened near Andromeda's core. The slow change in these orbits also reveals that the central black hole has been in place for a very long time. Its influence has shaped the region for billions of years. Stars have come and gone, some drifting inward, others moving outward. But the overall structure has remained consistent. This consistency indicates that the black hole formed early in the galaxy's history, likely during the first stages of Andromeda's development. Studying these swirling stars doesn't just help us understand Andromeda. It also influences how astronomers interpret the centers of other galaxies. Andromeda provides a relatively close example of a galaxy with a massive central black hole. With this knowledge, researchers can look at other galaxies and recognize similar patterns. The behavior of stars near their centers can reveal hidden masses elsewhere, even when direct observation is impossible. Getting a clear look into the center of a distant galaxy might sound like an impossible task, especially when that galaxy lies more than 2 million light-years away. Yet, astronomers have found ways to peer through the crowded glow, the dust, and the distance to study the details hidden inside Andromeda's core. The process didn't happen all at once. It came from decades of improving technology, new methods for studying light, and creative approaches to gathering information from places humans will never physically reach. Each tool acted like a new pair of eyes, adding clarity that wasn't possible before. By using these cosmic eyes, astronomers uncovered details about Andromeda's central region that once seemed out of reach. Looking into any galaxy's center is challenging because the cores are bright and dense. Light from millions of stars blends together, making it difficult to distinguish individual ones. Dust clouds also block certain wavelengths, especially in visible light. That means the clearest views require instruments that can look beyond what the human eye can see. Early observations relied on optical telescopes, which offered some insight but lacked the resolution needed to separate the crowded stars. Over time, astronomers developed better detectors and more advanced techniques that made it possible to extract details from the light that reaches Earth. One of the first major improvements came from the use of large ground-based telescopes equipped with spectrographs. These instruments separate incoming light into its component wavelengths, revealing patterns hidden within. Even though the view might appear blurred due to Earth's atmosphere, the information contained in the light can still show how stars move. These early spectroscopic measurements hinted at the rapid motions near the center, even before high-resolution images were available. Spectroscopy allowed astronomers to treat the light not just as something to admire, but as a source of measurable data. Every shift in wavelength gave clues about velocity, temperature, and composition. Atmospheric distortion limited what ground-based instruments could do, but scientists found ways to work around this. They developed adaptive optic systems that measure how the atmosphere distorts incoming light and then adjust mirrors in real time to counteract that distortion. This technology made distant stars appear sharper, allowing astronomers to examine regions that would otherwise be blurred. When adaptive optics were applied to observations of Andromeda, the central region became clearer. Stars that once blended together in a single bright patch began to separate into individual points. This improvement helped reveal the structure of the double nucleus and the distribution of stars near the core. While adaptive optics improved ground-based views, the launch of the Hubble Space Telescope transformed the study of galactic centers. For the first time, astronomers had access to images taken outside Earth's atmosphere, where no turbulence could blur the view. Hubble's sharpness made it possible to resolve structures in Andromeda's core that ground-based telescopes struggled to see. The double nucleus became unmistakable. The shapes of the central brightness peaks were mapped with precision. The detail in the images allowed astronomers to identify separate groups of stars, measure light gradients, and build models that matched the observations. Hubble's images also helped refine the estimates of the central black hole's mass. By observing how light changed across the core, astronomers could determine how fast stars were moving based on subtle shifts in brightness. Combining these shifts with models of stellar motion provided better constraints on the gravitational field. The relationship between distance from the center and stellar velocity became clearer, making the case for the black hole even stronger. Beyond optical wavelengths, astronomers turned to infrared light. Infrared telescopes reveal details that remain hidden in visible light due to dust. Dust grains absorb and scatter visible light, but infrared light passes through more easily. When Andromeda's core was examined in infrared, new stars appeared in regions previously obscured. These stars showed the same signs of rapid motion observed in visible wavelengths, confirming that the gravitational field extended into areas hidden behind dust. Infrared data also offered insight into the temperature and age of stars in the central cluster, revealing a mix of older populations and smaller groups of younger stars. Space-based infrared observatories added even more clarity. Instruments like the Spitzer Space Telescope provided infrared images of Andromeda that complemented the detailed optical data from Hubble. While Spitzer didn't have the same spatial resolution, it revealed the distribution of dust and cool stars in the galaxy. Understanding where dust collects helped astronomers interpret the visible and infrared data more accurately. Some parts of the core that looked unusually dim in optical images turned out to be obscured by dust rather than truly faint. When the dust maps were combined with star maps, researchers gained a clearer picture of how the central region is arranged. Radio observations contributed another perspective. Even though Andromeda's black hole is quiet, it emits faint radio signals from the small amount of material that occasionally falls inward. Instruments like the Very Large Array detected these faint emissions. The signals were subtle, but they indicated a compact source. Radio waves are unaffected by dust, allowing astronomers to pinpoint the location of the black hole more precisely than in visible light. By measuring the size and shape of the radio source, scientists could confirm that it matched expectations for a supermassive black hole with a very low accretion rate. As radio telescopes improved, interferometry techniques allowed multiple telescopes to be combined into a single, larger instrument. This method creates extremely high-resolution observations by linking telescopes across large distances. When interferometry was applied to Andromeda, the radio source near the core became even more defined. The data showed a structure consistent with a quiet black hole rather than a cluster or another type of compact object. Although the black hole itself could not be imaged directly, the radio source marked its position with enough accuracy to match the stellar motion data. X-ray observations added yet another layer. Even dormant black holes occasionally produce small amounts of X-ray radiation when hot gas drifts inward. Andromeda's core has faint X-ray emissions that originate near the black hole. These emissions are not strong, but they reinforce the idea that the central object is compact and gravitationally intense. The X-ray data also reveal the presence of hot gas in the surrounding region. Knowing how much hot gas is present helps astronomers estimate how much material could potentially fall toward the black hole, offering clues about why it remains quiet today. Combining observations across different wavelengths turned out to be one of the most important strategies. Each wavelength reveals a different part of the picture. Optical light shows older stars and their distribution. Infrared light exposes stars hidden behind dust. Radio waves mark the location of the compact central object. X-rays show hot gas and occasional outbursts. When all of these pieces are brought together, the view becomes far clearer than any single method could provide. The galaxy's core is no longer just a bright blur. Instead, it becomes a detailed environment filled with measurable structures and well-defined motions. Computer modeling continued to advance as observational data improved. Astronomers didn't rely solely on images or spectra. They built simulations that used all the available data as input. These simulations recreated the gravitational environment of Andromeda's core, showing how stars moved under different assumptions. When they included a supermassive black hole of the estimated mass, the simulations reproduced the observed velocity curves, orbital shapes, and brightness distributions. When they removed the black hole, the models fell apart. The stars didn't move fast enough or follow the expected orbits. The consistency between simulation and observation offered compelling confirmation. As computational techniques became more robust, astronomers applied them to the double nuclear structure, attempting to understand how such an arrangement could remain stable for long periods. The models showed that a ring or disk of stars orbiting around a massive central object could produce the appearance of two brightness peaks when viewed from Earth. Small variations in the orbits could create the offset appearance. Without the black hole, the ring would not hold its shape. The orbits would drift and merge into a single cluster. The stability of the double nucleus depended on the massive anchor at the center. Alongside these advances, astronomers refined measurements of the galaxy's bulge. The bulge is a large, rounded structure surrounding the core, filled with older stars. Understanding the bulge helps determine how much of the gravitational influence comes from stars and how much comes from the black hole. By mapping the density of the bulge and comparing it to the observed motions, researchers could separate the contribution of the black hole from the contribution of the surrounding stars. The bulge adds significant mass, but it cannot explain the sharp increase in stellar velocities near the center. That spike contains the signature of the black hole. Newer telescopes on the ground continue to improve our view of Andromeda's core. Extremely large telescopes equipped with the latest adaptive optics systems now offer resolution approaching that of space telescopes. These instruments can track motions of individual stars with increasing precision, extending the timeline of observations that began decades ago. Long-term datasets are especially valuable because they reveal how stars move over time rather than in single snapshots. When the paths of stars are traced over years or decades, their orbits become clearer. Those orbits reflect the underlying gravitational environment in a direct way. Peering into the core with these cosmic eyes requires constant refinement. No single observation captures everything. Instead, each new measurement fills in a missing detail. As data accumulates, the view sharpens. The bright central region becomes a structured environment, with stars moving in patterns that make sense when interpreted through the lens of gravity. The black hole itself remains hidden, but its influence shows up everywhere around it. Reflecting on how much these tools have revealed makes the galaxy feel a little more familiar. Even though Andromeda is enormous and distant, the ability to study its center in such detail creates a sense of connection. It no longer feels like an unreachable blur. It becomes a place with movement, structure, and a hidden object shaping everything around it. The instruments developed over the past century have made it possible to explore regions that once seemed hopelessly out of reach. As the view continues to improve, the details of Andromeda's core grow clearer. More precise measurements of stellar motion will refine the estimate of the black hole's mass. Better infrared imaging will reveal stars even closer to the center. Future radio arrays will map the compact radio source with greater accuracy. Each improvement pushes the boundary of what can be known without ever leaving Earth. Thinking about what happens near the edge of a supermassive black hole can feel intimidating at first, especially when the object in question sits inside the core of a neighboring galaxy. Yet, the region surrounding Andromeda's central black hole isn't a chaotic scene filled with constant destruction the way popular stories often describe it. Most of the time, it's an extremely quiet place. Nothing about it resembles the glowing disks and violent jets associated with more active black holes. Instead, the environment is shaped by slow interactions between stars, gas, dust, and the gravitational field that steadily guides their behavior. Even the area closest to the event horizon, the point beyond which nothing can return, follows rules that are stable and predictable. Understanding these rules helps create a clearer picture of what truly takes place near the boundary of the giant hidden inside Andromeda. The first thing to recognize is that very little material actually reaches the event horizon. This might sound surprising considering the enormous gravitational pull, but black holes do not automatically consume everything around them. Objects need to lose angular momentum to fall inward. Most of the stars and gas near the center of Andromeda follow orbits that keep them comfortably distant from the point of no return. They travel in paths shaped by the black hole's mass, but they are not on trajectories that lead them directly inward. The region around the black hole is mostly empty space. Stars are far apart compared to their size. With billions of years passing between close encounters, the chances of a star drifting too close are extremely small. Even gas clouds rarely approach the event horizon. Gas moves through the central region in clumps and streams, but those clumps are often thin, and their orbits keep them from plunging inward. Only in certain situations, such as when two clouds interact or when gravitational nudges accumulate over long periods, do small amounts of material drift close enough to be captured. When that happens, the material accelerates, heats up, and becomes part of a brief flow directed toward the black hole. For Andromeda's central black hole, these events are infrequent, which explains why the region is so dim. Before material can cross the event horizon, it enters a region where gravity increases rapidly. The closer something gets, the more dramatically its path bends. If the object is small, like a dust grain or a tiny gas particle, its motion becomes dominated entirely by gravity. It begins to fall inward in a spiraling path. But even during this stage, the process is calm. There's no sudden drop, no violent tearing apart unless the object gets close enough to experience strong tidal forces. For most pieces of material, the journey is steady, with energy gradually increasing as the object accelerates. The radiation produced during this process is faint in Andromeda because the amount of infalling material is low. Imagining the view from a safe distance can help. If you could hover many light years away from the event horizon, you would see stars moving in ordered paths. The black hole would appear entirely invisible. There would be no glowing surface, no boundary to mark where light disappears. The region would simply look darker than its surroundings. Only by tracing how stars and gas move would you notice anything unusual. Gravity would shape everything, but visually the environment would seem calm. Even the inner region where matter accelerates would not stand out unless sensitive instruments captured the faint radiation. Closer to the event horizon, the intensity of the gravitational field grows. Space bends more sharply, and time behaves differently. From the perspective of an outside observer, objects falling toward the black hole slow down as they approach the event horizon. Their light becomes stretched into longer wavelengths, gradually fading. If you could watch a particle fall, you would never see it cross the event horizon. Instead, it would appear to freeze near the boundary, growing dimmer until it disappeared. This effect doesn't mean the particle stops. It continues its fall. The change is only how the motion appears from a distance. Inside Andromeda's core, this effect plays out slowly and quietly because the black hole rarely pulls in anything large. When small amounts of gas do approach the event horizon, the energy produced is minimal. Instead of bright flares, Andromeda's black hole produces faint emissions that only specialized instruments can detect. These emissions confirm that material occasionally crosses the threshold, but the events are subtle. The region around the event horizon does not glow the way the central areas of more active galaxies do. Another important part of the story involves tidal forces. Tidal forces describe how gravity pulls more strongly on the part of an object closer to the black hole than on the part farther away. In small black holes, these forces can be strong enough to tear objects apart before they reach the event horizon. But in extremely massive black holes like the one in Andromeda, the event horizon is much larger and the tidal forces at that boundary are weaker. Objects could cross the event horizon intact without being torn apart immediately. It is only deeper inside that the forces become strong enough to stretch and compress matter dramatically. This detail makes Andromeda's black hole far gentler near the boundary than a smaller black hole would be. Stars rarely approach close enough to experience these forces, but when they do, the results can be spectacular. A star passing too near the black hole can be pulled apart in what is known as a tidal disruption event. The star stretches, breaks, and forms a stream of material that spirals inward. The radiation produced during such an event can be extremely bright. However, there is no evidence that Andromeda's black hole undergoes these events frequently. Its quiet nature suggests that stars pass at safe distances and that disruptions are extremely rare. If a star were to be torn apart today, the outburst would be noticeable across many wavelengths. But the calm environment implies that nothing like that is happening at the moment. While the region near the event horizon remains quiet most of the time, the gravitational environment still affects the larger galactic center. Gas clouds drift around the region, influenced by the black hole's mass. Occasionally, they collide or interact, and these interactions can send material inward. Each time that happens, a small amount of radiation escapes into space before the material falls beyond the event horizon. This radiation is faint but detectable, forming part of the signature astronomers use to confirm the presence of the black hole. The low level of activity is one reason Andromeda's core appears so gentle compared to active galactic nuclei. Its black hole simply doesn't receive enough fuel to produce intense emissions. If we shift perspective and imagine what a spacecraft would encounter as it approaches the core, the journey would feel uneventful for a long time. At far distances, the gravitational pull of the black hole blends with the pull from the bulge and disk. Only gradually would the spacecraft begin to feel the dominance of the central mass. The surrounding stars would appear to move in predictable orbits. Nothing about the environment would suggest that a massive, light-trapping object lies ahead. Even at relatively close distances, the black hole would remain hidden. It would blend seamlessly into the background of stars. Moving closer, the gravitational field grows stronger. The spacecraft's path would begin to curve more sharply toward the center, but the curvature would not feel abrupt. It would be a steady pull, gradually increasing over time. The spacecraft would accelerate, heading inward without encountering much material. The emptiness of space near the event horizon means there is little to collide with. The environment is strikingly serene despite the gravitational intensity. If the spacecraft carried instruments designed to measure energy levels, it might detect faint X-ray or radio emissions from particles spiraling inward. These emissions come from material that heats up as it falls, but they remain weak in Andromeda because there is so little of that material. The signals would grow stronger only when passing close to the region where particles reach high speeds. Even then, the emissions would remain modest compared to those from active galaxies. Approaching the event horizon, the spacecraft's clock would continue ticking normally, but observers watching from afar would see the clock slow down due to gravitational time dilation. The effect becomes more pronounced near the boundary. From the spacecraft's perspective, however, nothing unusual would happen when crossing the event horizon. There would be no visible boundary, no sudden change in motion. Only deeper inside would the forces grow strong enough to distort space severely. The physics within that region remains beyond direct observation, but general relativity provides predictions for how space and time behave. Staying outside the event horizon, the environment remains governed by classical gravitational dynamics. Each object responds to the curved space around the black hole. The swirling stars that astronomers study never approach this boundary closely. Their orbits keep them in stable loops far from the point where tidal forces grow extreme. Because of this, the visible environment around Andromeda's black hole remains dominated by the motion of stars rather than by dramatic inflow of matter. Gas that does approach the event horizon follows predictable patterns. It heats slowly, sometimes emitting small flares before disappearing. These flares do not last long and are difficult to detect at great distances. They contribute to the faint X-ray glow observed near the center. The glow is not bright enough to overshadow the starlight, but serves as a subtle mark of the black hole's presence. The event horizon itself remains the most mysterious part of the black hole. It marks the boundary beyond which no information escapes. From the outside, everything becomes invisible once it crosses. Because Andromeda's black hole is quiet, the event horizon doesn't interact with large amounts of material. It waits silently, influencing the motion of everything in the region but rarely displaying the kind of energetic behavior that would draw attention. This quietness makes the black hole difficult to detect without careful measurements. Yet, its influence reaches far beyond its boundary. In the broader environment around the event horizon, gravity helps shape how stars and gas distribute themselves. Over billions of years, the patterns we see today reflect the long-term behavior of objects responding to the central mass. Stars gradually migrate through the region due to gravitational encounters with each other. Some drift outward, some move inward. The overall density of the central cluster reflects this slow movement. Although the black hole does not feed actively, it remains a central organizing force, contributing to the stability of the bulge. Studying what happens near the event horizon also helps astronomers understand why Andromeda's core appears so different from those of more active galaxies. Active nuclei often glow brightly because their black holes consume large amounts of material. These feeding events create hot, luminous disks and powerful jets. Andromeda's black hole lacks a constant supply of fuel, leaving it in a low-activity state. It produces only faint emissions, allowing the starlight to dominate the central region. This contrast helps researchers compare different types of galaxies and understand the factors that influence black hole activity. Reflecting on the quiet region near Andromeda's event horizon adds another layer to the story of the galaxy's center. The black hole may be enormous, but its behavior today is gentle. It affects everything around it through gravity rather than bright emissions. The environment near the event horizon follows consistent rules, making the region predictable in ways that can be comforting rather than intimidating. The giant remains hidden behind starlight and dust, shaping space silently. Despite the size of the black hole inside Andromeda, the region surrounding it behaves with a quiet steadiness that feels almost unusual when compared to the activity seen in other galaxies. Many people imagine a supermassive black hole as something restless, constantly pulling in material, erupting with bursts of energy, or reshaping its environment in dramatic ways. Andromeda's central black hole doesn't match that image at all. Instead of producing powerful jets or blazing emissions, it sits in the middle of a busy galactic core, stirring very little. Its influence is undeniable, but its actions are measured. It holds the kingdom of stars around it in place without announcing itself through bright or violent events. This contrast between enormous mass and gentle behavior gives the region an unexpected sense of calm. The idea that a supermassive black hole could be quiet may seem surprising because many well-known examples behave very differently. In active galaxies, material flows inward at high rates, forming a swirling accretion disk that heats to extreme temperatures. That heat produces tremendous amounts of radiation. In some galaxies, jets of high-energy particles shoot out at nearly the speed of light. These active nuclei outshine the rest of their galaxies by orders of magnitude. Anyone looking at Andromeda's center, however, sees none of that. There is no glaring spot brighter than the surrounding stars. There are no jets shooting into space. Nothing lights up the region in an obvious way. Instead, the black hole works quietly, influencing its surroundings through gravity more than anything else. One reason for this quiet behavior is the lack of available material for the black hole to feed on. Gas in the central region is thin and sparse compared to what is present in more active galaxies. The stars orbiting nearby follow stable paths that keep them at safe distances. Without frequent close encounters, they do not send material toward the center. Even when dust or gas drifts inward, the amounts are small. There is little for the black hole to consume, leaving it in a mostly dormant state. This dormancy doesn't mean the black hole is inactive. It still emits faint radio and X-ray signals when tiny amounts of matter fall toward the event horizon. But those emissions stay weak, requiring sensitive instruments to detect. Some galaxies enter active phases because mergers or interactions send large amounts of gas inward. When galaxies collide, gas clouds compress and lose energy, falling toward the center where the black hole consumes them. Andromeda, however, is not currently undergoing a major merger. It has absorbed small galaxies in the past, and evidence of those events appears in the form of stellar streams and the distribution of stars in the halo. Those mergers almost certainly delivered fuel to the black hole long ago, but today the supply has dwindled. Without a fresh influx of gas, the black hole has entered a quiet phase that could last millions of years. Even though the black hole is quiet, its gravitational influence remains strong. It shapes the inner orbits of stars, contributes to the stability of the bulge, and anchors the central region. These effects happen slowly, without dramatic bursts. The black hole stirs its kingdom gently, guiding the stars without disrupting their paths. From a distance, the region looks calm. Even up close, if anyone could observe it directly, the lack of glowing material or violent motion would make the black hole appear less like a monster and more like a patient, seated force. Astronomers sometimes describe Andromeda's black hole as underfed. In the context of cosmic structures, feeding determines how active a black hole appears. When a black hole receives a steady stream of material, its energy output increases dramatically. When the supply is low, the energy output drops. Andromeda's feeding rate is extremely low. This low activity puts the black hole in a category similar to the one found in the Milky Way's center. Both galaxies host supermassive black holes that behave quietly, radiating at weak levels compared to their potential. These black holes remain far below the brightness they could achieve if provided with abundant material. Thinking about how rarely the black hole consumes anything helps explain its calm appearance. Most of the time, stars pass by at safe distances, and gas clouds follow orbits that prevent them from falling inward. Only occasional interactions push material toward the event horizon. Even then, the amount is minimal. A grain of dust or a small clump of gas might release a brief pulse of energy as it spirals inward, but those pulses remain subtle. Instruments that can detect faint X-ray or radio signals catch these small moments, but they do not affect the overall brightness of the galaxy's core. In addition to the scarcity of material, the sheer size of the black hole affects how it interacts with the environment. Because Andromeda's black hole is so massive, the event horizon lies at a greater distance from the center than in smaller black holes. The tidal forces at the boundary are relatively weak. Large objects could cross the event horizon without experiencing destructive stretching until they are much deeper inside. This difference means that even when something approaches the event horizon, the region does not produce the strong flares associated with tidal disruption. Only material that gets extremely close becomes violently torn apart. Most material never reaches that point. Another aspect of this calm behavior is the structure of the central bulge. The bulge contains many older stars that move in predictable orbits. The motions of these stars rarely produce dramatic interactions. They drift through the region with steady speeds, maintaining the shape of the bulge. Their interactions with each other are gentle. This stability reduces the chances of material falling inward. As a result, the black hole remains quiet, illuminated only faintly by the minimal feeding it receives. Despite this quietness, astronomers continue to study the black hole to understand the details of its behavior. Measurements of radio emissions help determine how much material is falling inward. X-ray observations indicate how hot the infalling gas becomes. Spectroscopy reveals the motion of stars in the surrounding region. All of these observations help refine models of the black hole's accretion rate and activity level. The numbers point consistently toward a low activity state. Comparing Andromeda's black hole to more active ones shows how significant the difference can be. In quasars, the accretion disks around supermassive black holes radiate so brightly that they outshine the entire galaxy. These disks produce light across a wide range of wavelengths. Jets extend outward for thousands of light years. The centers of these galaxies are anything but quiet. They stir their kingdoms with tremendous force, shaping their environments dramatically. Andromeda sits on the opposite end of that spectrum. Its black hole produces none of the typical signatures of a quasar. It behaves more like a dark, stable mass balancing the central region. There is another important reason why Andromeda's black hole stirs its surroundings gently rather than violently. The gas in the central region is relatively cool and diffuse. In active galaxies, gas clouds collide frequently, causing the gas to heat up and move inward. These collisions feed the black hole. In Andromeda, the lack of dense gas means fewer collisions. The gas remains in stable orbits instead of collapsing toward the center. Without the inward movement, the black hole receives little fuel. This condition creates a feedback loop. Low accretion keeps the core quiet, and the quiet core prevents gas from heating and falling inward. Astronomers often look for signs of past activity in galaxies. Bright emission lines in the surrounding gas can indicate that a black hole once produced strong radiation. Some galaxies show shells or bubbles created by past outflows. Andromeda does not show obvious evidence of recent energetic events. Its core appears to have been calm for a long time. This calmness suggests that the black hole's quiet phase is not temporary. It has persisted long enough to shape the current appearance of the central region. Thinking about this kind of calm behavior can shift how people understand black holes. Instead of viewing them solely as destructive or chaotic, Andromeda's black hole demonstrates how they can act as stable components of galaxies. Their gravitational influence does not always produce violent results. In many cases, including this one, the black hole is more like a central counterweight, keeping the system balanced. Although the black hole rarely stirs its kingdom through feeding events, its mass still affects the distribution of stars and the transfer of energy within the bulge. Stars passing through the region occasionally interact gravitationally, exchanging momentum. These interactions can push stars slightly inward or outward, slowly adjusting the density profile of the central cluster. Over time, the black hole helps maintain the structure by anchoring these interactions. Even without energetic outbursts, its presence remains essential. The long-term stability of Andromeda's core creates a valuable environment for studying how galaxies behave when their black holes are quiet. Many galaxies throughout the universe contain central black holes in similar states. These quiet phases may persist for millions or billions of years. Understanding the details of Andromeda's core provides insight into what drives galaxies to become active or remain inactive. It also helps explain how galaxies evolve over time, transitioning between stages of high and low activity. By comparing Andromeda with other galaxies, astronomers can trace patterns in black hole growth. In active galaxies, black holes gain mass quickly, altering the structure around them. In quiet galaxies, growth slows dramatically. Andromeda's black hole appears to have reached a stage where it no longer grows quickly. Instead, it may only gain small amounts of mass occasionally. This slow growth reflects the lack of available material. Over long time scales, the black hole may still grow larger, but the rate will remain low without significant events that funnel gas inward. One useful perspective involves thinking about what would be required to awaken the black hole from its quiet state. A major galactic collision could compress gas and send large amounts toward the center. As Andromeda moves toward the Milky Way, such a collision will eventually occur. This future event may provide the black hole with enough fuel to become active again. But for now, nothing nearby disturbs the calm. The stars continue their ordered orbits. The gas remains spread thin, and the black hole stays in its quiet phase. Even when the black hole does interact with nearby material, the effects remain subtle. A passing gas cloud might heat slightly and emit a faint burst of radiation. A tiny clump might spiral inward, releasing energy before crossing the event horizon. These events occur rarely and do not change the overall brightness of the core. The black hole acts almost indifferent, stirring its kingdom only through gentle gravitational influence rather than violent outbursts. This quiet behavior highlights a broader truth about galaxies. Not every massive object behaves in a dramatic way. Many processes unfold slowly, consistently, and predictably. The central black hole in Andromeda offers a good example of how a massive presence can shape its surroundings without constant activity. The quiet state of Andromeda's central black hole has puzzled astronomers for years, not because silence is unexpected in the universe, but because an object of such extraordinary mass seems like it should behave more dramatically. It has the potential to consume vast amounts of material, sculpt its surroundings through intense energy output, and shine across enormous distances. Yet it does none of those things today. Instead, the environment around it remains steady. The radiation is faint, the inflow of material is minimal. The stars passing nearby do so without disruption. The entire region feels peaceful in a way that does not match the reputation black holes have in popular imagination. This strange calm surrounds a beast that could, under different conditions, become one of the brightest and most powerful objects in the local group. One of the clearest explanations for this calm lies in the limited supply of material available for the black hole to consume. Feeding a black hole requires more than just nearby gas. The material needs to lose angular momentum so that it can spiral inward. Most of the gas in Andromeda's central region follows orbits that keep it at safe distances. Without frequent collisions or disturbances, that gas remains stable. The black hole does not possess an automatic ability to draw nearby matter inward. Gravity alone is not enough to break stable orbits. Only when something disrupts those orbits, such as a passing star, a shock wave, or a merger, does material drift closer to the center. Those disruptions are rare in Andromeda today, which means the black hole receives almost nothing to feed on. Even more striking, the stellar density near the core is high, but not in a way that regularly generates collisions. Stars remain far apart despite the crowded environment. If two stars pass close enough to each other to alter their trajectories, the change is usually minor. The chances that a star will be flung toward the event horizon through these interactions are incredibly small. In most cases, stars adjust their orbits gradually without losing enough momentum to fall inward. This orderly motion contributes to the black hole's quiet state. It acts as a stabilizing pattern that prevents dramatic events from happening often. Another factor contributing to the unusual calm is the temperature and distribution of the gas. The gas in this region tends to be cooler and more diffuse than in galaxies with active black holes. Cooler gas moves more slowly, but it does not collapse inward unless disturbed. Instead, it drifts in stable patterns around the core. Without the higher pressures and collisions found in more active galactic centers, the gas lacks the energy required to flow toward the black hole. In this environment, the black hole waits silently. It exerts gravity over a vast region but receives no substantial fuel. Scientists have compared Andromeda's core with that of the Milky Way. Because both galaxies host black holes in quiet states, the similarities are striking. In both systems, the central black holes rarely feed. Their emissions remain faint. Their surrounding structures appear stable. Some researchers believe these quiet phases represent a common stage in the life cycle of galaxies. After initial periods of high activity fueled by abundant gas and mergers, galaxies settle into quieter states where black holes consume little. This long, quiet period may span billions of years, with brief moments of activity occurring only when new material becomes available. Even though the black hole in Andromeda lies dormant in many respects, it still creates subtle effects that extend throughout the core. The gravitational field remains strong, guiding stars into long-term orbits. These orbits create the double nuclear structure that puzzled astronomers until they realized the stars were arranged in a disc-shaped pattern influenced by the black hole. The stability of that pattern depends on the persistent presence of the central mass. If the black hole were smaller or missing, the structure would drift apart. Its quietness does not diminish its role. Gravity continues to shape the region in predictable ways. Observations across different wavelengths confirm the low activity level. Optical observations show no bright emissions that would indicate a large, hot accretion disk. Infrared images reveal a stellar population that behaves consistently with a quiescent environment. Radio measurements detect only a faint signal produced by small amounts of material spiraling inward slowly. X-ray observations find a weak glow near the core. Each type of data matches the profile of a black hole that receives almost no fuel. This consistency across wavelengths reinforces the idea that the black hole is sleeping rather than temporarily inactive. When astronomers examine the temperature of the gas near the core, they find that it is not heated to the intense levels associated with active nuclei. Instead, the gas remains relatively cool. This coolness limits the amount of X-ray radiation emitted from the region. Hot gas would produce a stronger X-ray signal. The faint glow detected near the center fits with the idea that only small amounts of gas occasionally approach the event horizon. These faint emissions resemble a soft whisper rather than a roar, signaling minimal activity. Understanding how dormant the black hole is raises questions about its past. Evidence from the structure of the bulge, the distribution of stellar populations, and the history of mergers in Andromeda suggests that the black hole was more active long ago. During early stages of the galaxy's development, gas was more abundant. Stars formed at higher rates. Mergers brought in new material. All of these factors could have fed the black hole more regularly. If it experienced periods of high activity billions of years ago, it may have produced energetic outflows and bright emissions that shaped the central region. The quiet appearance today does not erase that history, it simply represents a later stage in the black hole's life cycle. Some researchers look for signs that the black hole may become active again in the future. The most likely scenario involves a major interaction such as the upcoming collision between the Milky Way and Andromeda. When these galaxies merge, the gas in both systems will collide, compress, and lose momentum. Much of that gas will fall toward the merged core, providing a substantial amount of material for the black hole to consume. In that future era, the black hole may awaken from its long sleep, becoming far brighter than it is today. But for now, nothing in the immediate environment triggers such activity. While the black hole remains asleep, it behaves more like a central weight than an engine of energy. It anchors the motion of nearby stars, smooths out irregularities in the gravitational field, and maintains the long-term stability of the bulge. This role is just as important as the dramatic behavior of active black holes. Without this quiet gravitational anchor, the central region would not behave the way it does. The stars would not follow their stable paths. The bulge might not maintain its current shape. The double nucleus would not hold together. The calmness of the black hole supports the broader order of the galaxy's core. Many people find it counterintuitive that something capable of extreme violence appears so gentle most of the time. The calmness of Andromeda's black hole, however, shows that black holes do not always behave as destructive forces. Their influence depends heavily on their environment. If material flows freely toward them, they respond with bright emissions and energetic processes. If the environment lacks material, they become almost invisible. This difference highlights how important the surroundings are in shaping the behavior of a black hole. Considering the scales involved can help put this calmness into perspective. The black hole has a mass around 100 million times that of the Sun. Its event horizon spans a region far larger than the orbit of Earth. The gravitational influence extends across thousands of light years. Yet all of this power remains largely undemonstrated visually because the black hole is not interacting with much of the environment at the moment. Its potential for activity remains immense, but the conditions required to trigger that activity are absent. The result is a quiet presence that commands the region through mass alone, rather than through energy output. Though dormant, the black hole still affects the motion of stars in subtle ways. Stars near the core shift position slightly over long timescales. These shifts reflect gravitational interactions within the cluster. Stars closer to the black hole move faster, following tighter loops. Stars farther away move more slowly. The gradient of speeds traces the shape of the gravitational field. The consistency of this gradient indicates a stable environment. Over decades of study, astronomers have observed no dramatic changes in the central region. The patterns remain intact, reinforcing the image of a sleeping black hole that exerts steady but quiet influence. Some stars follow elongated orbits that bring them closer to the black hole at certain points. When this happens, the gravitational pull increases briefly, speeding the stars up before sending them outward again. These brief moments reveal the strength of the black hole's mass. But even during these close passes, the stars remain intact. The black hole's tidal forces at the distances of their orbits are not strong enough to disrupt them. The result is a smooth dance of stellar motion rather than violent events. The black hole acts as the center around which all of this motion happens. Yet, it never displays the brightness associated with feeding. If someone imagined approaching the central region, the visual experience would not resemble science fiction depictions. Instead of a glowing disk or beams of radiation, they would see a dense cluster of stars shining against the dark of space. The black hole itself would not be visible. It would appear only as a place where no light is seen. The calm around it would be both surprising and reassuring. Nothing in the immediate view would signal danger unless one moved extremely close to the event horizon. The region's stability reflects billions of years of evolutionary balance. This strange calm provides astronomers with a unique opportunity. Because the black hole is quiet, the starlight near the center is not overwhelmed by bright emissions. This makes it easier to track star motions and study the gravitational environment. In more active galaxies, the bright core can obscure details of the surrounding stars. But in Andromeda, the faintness of the black hole's emissions allows astronomers to measure velocities with greater accuracy. This precision has helped refine the mass estimate of the central black hole and map the distribution of stars in the bulge. Scientific curiosity about Andromeda's calm black hole continues to grow because it reveals what supermassive black holes look like during long periods of inactivity. The galaxy is massive, structured, and vibrant in many regions, yet the core behaves with an unusual softness. That softness becomes even more interesting when compared to what might eventually happen during the future merger with the Milky Way. The quiet today may serve as a contrast to a much more active period billions of years from now. When astronomers look closely at the region surrounding Andromeda's black hole, one of the most striking elements they find is the presence of tightly packed star clusters that orbit just far enough from the central mass to remain stable. These clusters behave like small cities of stars moving together through a gravitational landscape shaped by the enormous object at the center. Their motions appear coordinated when viewed from afar, but each star follows its own path, influenced by gravity from both the surrounding cluster and the black hole itself. This balance creates a pattern that remains intact over incredibly long timescales. Understanding how these clusters stay together while orbiting so close to a supermassive black hole adds another layer to the story of Andromeda's calm core. A useful starting point involves thinking about how clusters maintain their structure. Each star within a cluster exerts gravity on every other star. These gravitational pulls create a collective bond that holds the cluster together. But when a cluster moves near a supermassive black hole, it experiences additional gravitational forces that can stretch or compress it. The closer a cluster travels to the black hole, the stronger those forces become. If the cluster enters a region where these forces exceed the binding strength of the stars, the cluster can begin to lose members. Stars may drift away from the group or be sent onto new trajectories. In extreme cases, a cluster can be torn apart entirely. Yet, many clusters near Andromeda's center remain stable, demonstrating that they occupy regions where the balance between their internal gravity and the pull of the black hole is just right. Astronomers studying these clusters often begin by measuring their speeds. Faster motion indicates a closer orbit around the central mass. Slower motion suggests a more distant one. These measurements help determine how tightly bound the clusters are to the black hole. In Andromeda's case, the clusters near the core move quickly, but not at a speed suggesting imminent disruption. Their motion reflects their position within a gravitational environment that is strong but not destructive. The clusters travel through space as though following well-laid routes, with each star maintaining a path shaped by many interacting forces. The double nucleus structure becomes relevant again when considering the positions of these clusters. One of the brightness peaks observed in Andromeda's center is actually part of an elongated cluster of stars. This cluster forms a coherent group that orbits the central mass in an eccentric pattern. Its structure remains intact despite the gravitational influence of the black hole. The fact that such a cluster can exist near the core helps astronomers understand where the limits of the gravitational field lie. It provides a natural point of comparison for other clusters located farther out. Another aspect of these clusters involves their ages. Many of the stars in the central region are old, having formed billions of years ago. The clusters themselves have survived over long periods, which suggests they have been stable under the black hole's influence for much of the galaxy's history. Their long survival indicates that the gravitational environment of Andromeda's center has remained steady for ages. If dramatic changes had occurred frequently, such as large bursts of infalling material, the clusters might have been disrupted. Instead, they persist, demonstrating the consistent calm that defines the core. When researchers examine the density of stars within these clusters, they find that the clusters remain compact even near the black hole. The stars maintain short distances from one another compared to the broader bulge. This compactness helps strengthen the cluster's internal gravity. A loosely bound cluster would be more vulnerable to the black hole's tidal forces. But Andromeda's clusters remain dense enough to weather those forces. Their density helps them act as cohesive units, not easily disturbed by external influences. Thinking about what it would be like to watch these clusters from a vantage point near the core reveals a scene filled with steady motion. The clusters orbit the black hole at specific distances, following paths dictated by the mass at the center. Within the clusters, stars move around one another, forming a dynamic environment where gravitational interactions occur constantly. Yet these interactions remain predictable rather than chaotic. The stars move in ways that reflect the long-term stability of the system. One way astronomers study these clusters is by mapping the light they emit. The brightness patterns help determine how many stars the clusters contain, how they are arranged, and how they move. Brightness gradients offer clues about how strongly the clusters are bound. A steep gradient suggests a dense core of stars. A more gradual gradient indicates a cluster that may be more loosely bound. In Andromeda's case, many of the clusters near the center show signs of strong binding. Their light profiles match what would be expected from stable groups of stars orbiting a massive central object. Another important aspect involves how these clusters formed. Some may have originated far from the black hole and migrated inward over billions of years through gravitational interactions within the galaxy. Others may have formed in the central region itself when gas clouds collapsed to produce new stars. If clusters formed near the core, they would have had to contend with the black hole's influence from the beginning. Their existence implies that the gravitational environment allowed star formation to occur without immediate disruption. This helps astronomers reconstruct the history of the central region, demonstrating that the black hole has allowed stable structures to exist around it for a long time. Not all clusters near the center behave identically. Some drift close to the black hole over long periods, while others slowly move outward. These shifts occur due to interactions with other stars and clusters. Each encounter transfers small amounts of momentum, gradually altering the trajectories of the involved objects. Over millions of years, these small changes accumulate, reshaping the distribution of stars and clusters in the region. Yet, despite these slow shifts, the overall structure remains intact. The clusters that survive near the black hole do so because their binding strength and orbital paths keep them stable. One detail that often surprises people is how rarely stars within these clusters collide. Even though the clusters are dense, the stars are still separated by vast distances relative to their size. Collisions are extremely rare. Instead, stars move past one another, influencing each other through gravity but not through direct contact. These gravitational encounters shape the orbits of the stars and play a role in how the cluster evolves over time. The black hole's influence adds another layer to these interactions, guiding the entire cluster through space while allowing individual stars to drift toward or away from the center of the cluster. Astronomers also consider how clusters might behave if the black hole entered an active phase. Increased radiation or inflowing material could change the gravitational environment. However, because Andromeda's black hole remains quiet today, the clusters near the core experience little disruption. Their stable presence reflects the current inactivity of the black hole. This quietness provides an opportunity to study cluster dynamics in a relatively undisturbed environment. It offers a rare chance to see how stellar groups behave near a massive, compact object that exerts gravitational influence but does not produce strong radiation. If one imagines looking down on the central region from above, the star clusters would appear as bright, compact spots moving through a larger glow of starlight. Their motion would trace long arcs over time, looping around the center in consistent patterns. The black hole's presence would not be visible directly, but its influence would define the shape of these arcs. The clusters would move steadily without sudden shifts in speed or direction. This coordinated behavior reflects the maturity of the region. It has settled into a long-term equilibrium shaped by billions of years of gravitational interactions. In addition to clusters, individual stars sometimes travel near the black hole in isolation. These stars may form part of larger groups or move independently through the region. Their paths help refine the understanding of the gravitational field. By observing how stars accelerate as they approach the center and decelerate as they move away, astronomers gain insight into the mass distribution. These measurements support the conclusion that the black hole dominates the inner region. But the presence of stable clusters reinforces the fact that the environment remains gentle enough to allow long-term structures to persist. The edges of the clusters provide valuable information. Stars located on the outskirts of the clusters experience weaker binding forces compared to stars at the center. These outer stars are more susceptible to being influenced by the black hole. Some may be pulled slightly inward over long periods. Others may drift outward. The gradual reshaping of the cluster edges helps astronomers understand how the cluster responds to tidal forces. Andromeda's clusters appear resilient, resisting significant disruption because their central binding remains strong. Another factor that helps these clusters survive involves the way the central black hole interacts with the galaxy as a whole. The region around the black hole is not filled with high-pressure gas or bright radiation. This calm environment allows clusters to orbit without encountering harsh conditions. In more active galaxies, clusters near the core can be stripped apart by strong radiation or fast-moving material. Andromeda's quieter core offers a safer environment where gravitational interactions dominate over energetic ones. As researchers continue to measure the behavior of these clusters, they build models that simulate their long-term motions. These models demonstrate how clusters evolve under the influence of the black hole and the surrounding bulge. They show that clusters can remain stable for billions of years unless external forces disrupt them. These simulations also help predict how the clusters may behave in the future, especially as Andromeda slowly moves toward its eventual merger with the Milky Way. Considering the future, the clusters near the core may play a role in how the central region changes during the merger. Their distribution, binding strength, and motions could influence how material settles in the new combined core. But for the moment, they continue their slow, steady dance on the edge of the black hole's domain, revealing how stars organize themselves under the influence of massive central objects. When astronomers first realized that Andromeda is moving toward the Milky Way, the discovery felt both immense and strangely gentle. The speed involved, hundreds of thousands of kilometers per hour, sounds dramatic, yet the event it describes will unfold over billions of years. Nothing about it resembles the sudden collisions familiar in everyday experience. Instead, it is a slow process of drifting, stretching, and blending, a meeting between two enormous galaxies whose paths have been shaped by gravity since their earliest days. Thinking about this long approach adds context to everything happening near Andromeda's core, because the quiet black hole and the stable star clusters will one day experience a completely new environment shaped by the merger of two great spiral systems. The first step in understanding the future collision involves tracing the motion of Andromeda through space. Observations show that it is not simply moving toward the Milky Way by chance. Both galaxies are bound by gravity, drawn together because they reside in the same part of the local group. Their mutual attraction has been gradually pulling them closer for billions of years. Even though the universe is expanding, the gravitational pull within the local group is strong enough to overcome that expansion on local scales. As a result, the distance between the two galaxies decreases slowly over time, and eventually their outermost stars, halos, and gas will begin to interact before any part of the galaxies truly collides. Their dark matter halos will meet first. These halos extend far beyond the visible parts of the galaxies. They consist of diffuse, unseen matter that surrounds each galaxy like an enormous cloud. When the halos overlap, the gravitational environment changes subtly. Both galaxies will feel a stronger pull, and their motions will adjust accordingly. Nothing dramatic will happen right away. The stars in both galaxies are so far apart that their initial meeting will pass without direct collisions. Instead, the gravitational influence will begin to shift the shapes of the galaxies, pulling their disks into stretched patterns that resemble tidal distortions. Gas clouds within the galaxies will start to interact before the stars do. Gas behaves differently from stars because it can collide, compress, and heat. When the gas from the Milky Way meets the gas from Andromeda, the collisions will produce shock waves. These shock waves can trigger bursts of star formation. New stars may form in regions where gas compresses under pressure. This burst of activity could create clusters of young, bright stars, illuminating parts of the merging system. While the black hole in Andromeda remains quiet today, the additional gas funneled toward the center during the merger could cause increased activity later on. As the galaxies continue to approach, their disks will begin to bend and twist. The graceful spiral shapes that define both galaxies today will gradually lose their symmetry. Long tails of stars and gas may stretch outward as gravity pulls on the outer regions. These tidal tails are common in galaxy mergers and can extend for tens of thousands of light years. They form when stars and gas are drawn out from the edges of the galaxies as they pass by each other. Although these tails give the appearance of tearing, the process occurs smoothly over vast timescales. When the cores of the two galaxies finally draw close, the interaction becomes more intense. The central regions contain dense groups of stars, clusters, and gas. The gravitational pull between both cores will distort their orbits and accelerate the mixing of material. However, even during this phase, direct collisions between stars remain extremely unlikely. The space between stars is enormous compared to their size. Most stars will pass by one another without contact, experiencing only slight changes in their trajectories. Their paths will adjust according to the evolving gravitational field rather than through impact. The black holes at the centers of the two galaxies will play a major role during this stage. Andromeda's black hole and the Milky Way's black hole will eventually begin to move toward each other due to the changing gravitational environment. As the galaxies merge, these central objects will spiral inward, drawing closer together over millions of years. Their orbits around each other will shrink gradually as they transfer energy to the surrounding stars. Some stars near the two black holes will be flung outward into the galaxy, gaining momentum from the interaction. Others will fall inward, contributing to the slow tightening of the black hole orbit. During this period, the inflow of gas toward both black holes may increase. Gas clouds lose angular momentum more easily than stars and can funnel inward when disturbed. If enough gas reaches the central regions, the black holes could transition into active states. Bright emissions could appear as the gas heats up in accretion disks. These emissions might temporarily outshine large portions of the merging galaxies. The black hole in Andromeda, long dormant, could become significantly more active during this phase, shining more brightly than at any time in its recent history. The merger will continue beyond the initial encounter as the galaxies pass through each other. Their momentum will carry them apart after the first close approach, but gravity will pull them back together again. This back and forth motion may repeat several times. Each pass will stretch and warp the galaxies further. Their spiral arms will lose coherence. Their shapes will become elongated, twisted, and eventually blended. Over time, the distinction between the two galaxies will fade. Instead of two separate spirals, the system will begin to resemble a single larger galaxy with a new structure emerging from the remnants of the originals. Simulations suggest that the final merged galaxy will become an elliptical or lenticular system rather than a spiral. The motion of stars will shift from organized circular orbits into more random paths. The smooth disk and spiral arms that define Andromeda and the Milky Way today will disappear. In their place, a more rounded structure will form, populated by stars whose orbits crisscross in different directions. This change reflects how mergers redistribute energy among stars, altering their paths through gravitational interactions. The merging of the two central black holes will represent one of the final stages of the process. As the black holes draw close enough, they will begin losing energy through gravitational waves. These ripples in space-time carry away energy, causing the two black holes to spiral closer together. Eventually, they will merge into a single larger black hole. This merger will release a burst of gravitational waves detectable across the universe. However, the event will not produce visible light from the perspective of the stars orbiting nearby. The transition from two black holes to one will happen without a dramatic change in appearance. Long before the black holes merge, the stellar populations of both galaxies will mix. Some stars from the Milky Way will migrate into regions that were once part of Andromeda, while some Andromeda stars will settle into regions once dominated by the Milky Way. This exchange will continue until individual stars no longer reflect the origin of their parent galaxies. The mixing will contribute to the formation of the new galactic structure. The merged galaxy will contain stars of many ages and compositions, collected over the long histories of both systems. The future merger also raises questions about how the solar system will be affected. The answer depends on many factors, but simulations suggest that the solar system is more likely to drift into a new orbit within the merged galaxy, rather than being ejected or drawn toward the central black hole. The distances between stars are so large that direct collisions between star systems remain extremely unlikely. The merger will reshape the sky as seen from Earth, but the local environment of the solar system may remain relatively undisturbed on smaller scales. The night sky could eventually show bright streams of stars from Andromeda weaving across the view, offering a future vista far different from what people see today. Thinking about this merger from the perspective of Andromeda's quiet core adds another dimension to the story. The calmness that defines the black hole today will not last forever. The merger will supply it with new material. Gas from both galaxies will fall inward, potentially reigniting activity. The inflow could produce emissions far stronger than anything seen in the present. The dormant black hole may awaken briefly as its environment changes. This potential for future activity highlights how galaxies shift between steady periods and active stages depending on the availability of fuel. The star clusters near Andromeda's center will also experience changes. Some may be pulled into new orbits. Others may merge with clusters from the Milky Way. Their positions relative to the black hole could shift as the gravitational field evolves. Some clusters may even be disrupted if tidal forces become too strong during the merger. But many will survive, forming part of the new galactic core. Their motions will adapt to the combined gravitational influence of the merged system. Over long periods, the new galaxy that emerges from the merger will settle into a stable shape. The black holes will merge. The stars will adopt new orbits. The gas will settle into new patterns. The system will enter another quiet phase, though the details of its structure will differ from either parent galaxy. The calmness that Andromeda's black hole experiences today may return in a different form. The merged galaxy will be larger, more massive, and shaped by the history of both spirals. Imagining this entire sequence helps place the current state of Andromeda in context. The calmness near its core represents only one part of a long story. The galaxy has experienced active phases in the past and will likely experience new ones in the future. The collision with the Milky Way is a natural step in the evolution of both galaxies. It is not an abrupt or violent event, but a slow transformation that will reshape the local group. Comparing the black hole and the Milky Way with the one anchoring Andromeda reveals how two central giants can share the same fundamental nature, yet differ dramatically in scale, behavior, and influence on their surroundings. Both systems host supermassive black holes. Both sit at the hearts of spiral galaxies, and both shape the motions of nearby stars. Yet beyond these similarities, the two objects diverge in ways that reflect the histories of their galaxies and the conditions that shape them. Thinking about these differences offers a clear sense of how galaxies evolve in varied environments and why Andromeda's core looks and behaves differently from our own. A good starting point involves considering their sizes. The black hole in the Milky Way, known as Sagittarius A star, has a mass of roughly 4 million suns. That may sound enormous, and by everyday standards it is, but compared to the black hole in Andromeda, it is surprisingly small. Andromeda's central giant weighs in at more than 100 million solar masses, making it more than 20 times larger. This difference in mass creates a difference in gravitational influence. A more massive black hole curves space more strongly, affects larger surrounding regions, and provides a deeper gravitational well for stars to orbit. The Milky Way's black hole shapes a relatively small part of the galaxy's core, whereas Andromeda's has influence over a meaningfully larger region. Despite this size gap, the behavior of the two black holes today is surprisingly similar. Both lie in quiet states. Neither one consumes large amounts of material on a regular basis. Their accretion rates remain extremely low. Sagittarius A star occasionally produces brief flares when small amounts of gas fall inward, but these events are rare and faint compared to the activity of black holes in more energetic galaxies. Andromeda's central mass behaves in a nearly identical way, emitting only faint radio and X-ray signals. This shared calmness reflects the current environments of both galaxies. Neither system is offering its black hole enough material to trigger significant activity. The conditions around them keep them quiet. One of the most important differences concerns how close astronomers are to each black hole. The Milky Way's black hole is located about 26,000 light-years from Earth, making it much closer and easier to study in detail. Andromeda's black hole sits more than 2 million light-years away. That distance blurs fine details even when using the best telescopes available. Because of its proximity, Sagittarius A star has been observed with incredible precision. Astronomers have tracked individual stars orbiting the black hole, watching their paths bend and curve in real time. These observations offer direct proof of the black hole's presence. In Andromeda, similar tracking is possible, but on a larger scale, and the stars are farther from the black hole. The details are more difficult to resolve, but the patterns still reveal the presence of a massive object shaping their motion. These differences in proximity also explain why the Milky Way's black hole has been imaged in far greater detail. Using networks of radio telescopes spread across Earth, astronomers captured a direct image of Sagittarius A's shadow, the dark silhouette formed by the event horizon against the glowing material around it. Creating this image required extraordinary precision. Attempting the same feat with Andromeda's black hole remains a distant goal because the increased distance makes it far smaller on the sky. Even though Andromeda's black hole is much larger, its apparent size from Earth is too small for current instruments to resolve at the same level. Future improvements may change this, but for now, Sagittarius A provides the best opportunity to see what a quiet, supermassive black hole looks like up close. Thinking about why Andromeda's black hole is so much larger than the Milky Way's leads to questions about their histories. Growth for a black hole depends on how much material it receives over time. Galaxies that undergo frequent mergers or experience strong inflows of gas often host larger black holes because these events feed the central mass. Andromeda shows signs of a more active merger history than the Milky Way. Streams of stars and remnants of past collisions appear in its halo. These encounters may have provided gas and energy that helped its central black hole grow to its current size. The Milky Way has also experienced mergers, but the events may have been smaller or provided less fuel for Sagittarius A's prof. As a result, the black hole at the center of our galaxy did not grow as much. These different growth histories shape the environments around each black hole. The region surrounding Sagittarius A sure contains a cluster of young, massive stars. Some of these stars formed out of disks of gas orbiting the black hole. Their presence raises questions about how star formation can occur so close to such a massive object. The environment around Andromeda's black hole contains a more mixed population of stars, with many older ones dominating the view. This difference reflects the star formation history of each galaxy. The Milky Way has pockets of gas capable of forming young clusters near the core, while Andromeda's central region appears more settled, with less recent star formation and older stellar populations dominating the scene. In both cases, the stars nearest to the black hole help reveal how strong the gravitational field is. Around Sagittarius A, astronomers have tracked stars that complete orbits within decades, offering direct, precise measurements of the black hole's mass. One well-studied star, often referenced as S2, completes an orbit in about 16 years, swinging in close enough to provide valuable data about the curvature of spacetime near the event horizon. The ability to watch these orbits unfold has confirmed predictions from general relativity and provided insight into how black holes influence the motion of nearby stars. In Andromeda, the situation differs not because the physics is different, but because the scale is larger. The stars nearest to Andromeda's black hole orbit at greater distances and take longer to complete their cycles. Tracking those orbits is more difficult because the stars appear fainter and more closely blended from our viewpoint. Even so, the motion detected through spectroscopy and high-resolution imaging offers enough evidence to determine the mass of the central black hole. The stars move quickly enough to indicate a massive object, even if their paths cannot be tracked as precisely as those near Sagittarius A. Examining how each black hole influences its surrounding clusters provides another interesting comparison. Sagittarius A stir sits in a region filled with star clusters that contain hot, young stars formed in disks of gas near the core. Over time, these clusters move around the black hole in complex paths shaped by the gravitational environment. Andromeda's central region, however, contains the well-known double nucleus made up of two concentrations of older stars arranged in a disk surrounding the black hole. This structure arises from the gravitational field of the black hole shaping the orbits of stars in a long-standing disk. The presence of this double nucleus suggests a different evolutionary path for Andromeda's core, one that involves older populations rather than new bursts of star formation. These distinctions highlight how the size of the black hole and the availability of gas influence the character of the galactic center. The Milky Way's black hole, although quiet, has a nearby supply of gas that can occasionally be disturbed, producing flares. Andromeda's black hole has far less gas in its immediate vicinity, resulting in even fewer disruptions. This helps explain the extremely low level of activity in Andromeda's core today. It also hints at how the environments of galaxies evolve over time based on available fuel. Even though Sagittarius A is smaller, it shares the same fundamental process for feeding as Andromeda's black hole. Material approaching either black hole heats up and emits radiation before crossing the event horizon. The difference lies in how often this happens. In the Milky Way, small amounts of gas occasionally reach Sagittarius A, creating brief, weak emissions that can be measured. In Andromeda, even these small events are rare. The quietness of both black holes reflects their current lack of accessible material rather than any inherent difference in their behavior. When astronomers think about the upcoming merger between Andromeda and the Milky Way, the comparison between the two black holes becomes even more important. During the merger, both black holes will likely grow. Gas will fall inward from disrupted structures in both galaxies. The increased supply of material may awaken the black holes from their quiet states. They may produce flares, form accretion disks, and shine far more brightly than they do today. Eventually, the two black holes will spiral toward each other and merge, forming a single, larger black hole at the center of the combined galaxy. The mass of this merged black hole will reflect the sum of both giants, creating a central object far more massive than either one today. Before that future arrives, the comparison between the two black holes helps astronomers understand how galaxies like the Milky Way and Andromeda reach their current states. The size difference means that Andromeda's black hole exerts a stronger gravitational influence on its surrounding stars. This difference contributes to the structure of each galaxy's bulge. The Milky Way contains a boxy bulge shaped by internal dynamical processes, while Andromeda's bulge is smoother and more rounded, consistent with the influence of a larger central mass. These distinctions show how a black hole's size affects the long-term structure of its host galaxy. Studying the environments near both black holes also reveals differences in the distribution of dark matter. The Milky Way's dark matter halo influences the rotation curve of the galaxy on larger scales, but its central region remains dominated by the stellar bulge and Sagittarius A. Andromeda's rotation curve indicates that its dark matter halo is more extended and massive, influencing how stars move even closer to the core. These details suggest that Andromeda has accumulated more mass overall, which helps explain both its larger size and its larger black hole. By comparing these two systems, astronomers gain insight into how galaxies grow through mergers, star formation, and interactions with their environments. The Milky Way's smaller black hole reflects a quieter growth history, while Andromeda's larger black hole indicates a more active past. Both systems now reside in quiet phases, but their future paths will converge during the merger, creating a new galaxy shaped by the combined history of both spirals. Thinking about this comparison also helps people understand that black holes do not exist in isolation. Their behavior reflects the environment around them. Sagittarius A star is small but surrounded by gas and young stars. Andromeda's black hole is large but surrounded by older, more settled populations. These differences produce unique signatures that allow astronomers to distinguish one system from another, even when the fundamental physics remains the same. Thinking about a supermassive black hole in another galaxy might seem at first like an exercise in pure astronomy, something distant and technical that has little to do with everyday life. Yet, objects like the one deep inside Andromeda end up revealing far more about human perspectives than about the distant darkness itself. Studying something so remote forces people to confront time on scales that exceed any single lifetime, movement on scales that exceed personal experience, and forces so large that they reshape entire galaxies without sound or visible motion. The process of trying to understand such an object often becomes a reflection of how humans approach mystery, how they construct meaning, and how they grow comfortable with things that cannot be touched or seen directly. One of the clearest lessons from Andromeda's black hole comes from its quiet nature. Many expect something so massive to behave explosively, to dominate its environment with displays of energy and constant change. Instead, it sits in a long period of calm. This contrast challenges the assumption that power always needs to be loud or visible. Human expectations often connect strength with activity, as though stillness suggests weakness. Andromeda's core tells a different story. Its quietness reflects stability, not fragility. Its influence remains strong because of its mass, not because of any continuous outpouring of energy. Seeing something so powerful remain so quiet encourages a deeper appreciation for the form strength can take. Another important lesson emerges from the difficulty of observing the black hole directly. Everything people know about it comes from its influence on the things around it. Stars move in certain ways because of its gravity. Gas heats up as it falls inward. Light shifts in particular patterns because of the curvature of space near the dark center. This reliance on indirect evidence teaches patience and careful interpretation. Humans often prefer clear answers that can be seen directly or measured easily, but the universe does not always cooperate with those preferences. Understanding Andromeda's black hole requires trust in long-term observations, in combined data sets, and in models refined over decades. This method of discovery mirrors the process of learning in many areas of life, where answers do not arrive suddenly but slowly clarify through careful attention. Even the distance to Andromeda offers perspective. Light from its core takes more than 2 million years to reach Earth. That means everything seen today happened long before humans existed in anything resembling modern form. The quiet state of the black hole, the shape of the bulge, the distribution of star clusters, all of these features represent snapshots of a time unimaginably distant from the present. This realization helps place human lifespans into context. It doesn't diminish individual experiences, but instead emphasizes how brief human existence is compared to the age of the cosmos. Such a perspective can create a sense of humility, but it also highlights the remarkable fact that a species with such a short lifespan can study and interpret events older than itself by orders of magnitude. Studying Andromeda's central darkness also reinforces the value of asking questions, even when the answers feel far beyond reach. Early astronomers had no tools capable of detecting black holes. They couldn't measure the motions of distant stars with precision. They couldn't image galactic centers. Yet they still asked what lay inside these structures. They noticed patterns in brightness and motion that didn't fit expectations, and followed those questions through decades of improvement. This willingness to explore the unknown, even when success seems uncertain, reflects a quality that appears repeatedly throughout human history. The black hole teaches that curiosity is not weakened by distance or difficulty. It thrives precisely because the answers are hard to find. Another point of reflection comes from the slow pace of change around Andromeda's black hole. The environment near the core evolves over millions or billions of years. Stars drift inward or outward gradually. Gas clouds shift shape and density slowly. The region remains stable across timescales longer than the existence of entire civilizations. Humans, by contrast, experience rapid change. Technologies evolve within decades. Ideas shift within years. Personal lives transform even faster. Comparing these timescales can be grounding. It reminds people that not everything happens quickly and that some processes require patience beyond any individual lifetime. The universe continues unfolding on its own schedule, unaffected by human urgency. The intermediate space between the black hole and the larger galaxy also offers lessons in balance. Stars near the core follow orbits shaped by both the black hole's gravity and the mass of the surrounding bulge. Neither influence acts alone. Each star follows a path created by combined forces. The orbits remain stable because the environment is balanced. This interplay mirrors the way many human systems function. Rarely does a single influence shape an outcome. Most stable arrangements involve multiple forces, social, personal, environmental, interacting over long periods. Understanding these layered influences becomes easier when looking at how galaxies maintain order through a combination of many components. Even the star clusters near the black hole offer insight. They remain stable because their internal binding forces outweigh the tidal forces trying to pull them apart. Their stability depends on cooperation among their members, not competition. If the stars within a cluster drifted apart too much, the black hole's gravity could disrupt them. But because the stars remain closely bound, the cluster survives. This concept parallels the idea that communities withstand challenges more effectively when the members remain connected. Although the comparison is metaphorical, the underlying principle, strength through cohesion, appears consistently in both astronomy and human experience. Thinking about Andromeda's black hole also highlights the limits of knowledge. No instrument can see inside the event horizon. no measurement can reveal what happens once matter crosses that boundary. Humans must accept that part of the universe remains hidden, not because of technological limitations, but because the laws of physics prevent it from being observed. Accepting unknowns can be difficult. People often seek certainty even in situations where certainty is impossible. The black hole teaches that some boundaries cannot be crossed, and that accepting those boundaries is part of understanding the natural world. This acceptance does not reduce curiosity. Instead, it shapes it into a form that respects what can be known and what cannot. Another lesson arises from the long history of Andromeda's core. The black hole likely experienced periods of intense activity in the past. It may have consumed large amounts of gas, influenced star formation, and shaped the bulge during earlier stages of galactic evolution. Today, it rests in a quiet stage. The contrast between its past and present behavior reflects the idea that everything moves through cycles. Galaxies experience periods of growth, transformation, and calm. These cycles resemble the rhythms found throughout nature. Stars form, shine, and fade. Black holes grow and rest. Even human lives reflect patterns of activity and stillness. Recognizing these cycles can make it easier to understand change as a natural part of existence rather than an unexpected disruption. Considering the distant darkness also encourages reflection on scale. The black hole's mass, its gravitational influence, and the size of Andromeda all exceed human comprehension. Yet these enormous structures obey simple laws. Gravity shapes the motion of stars and gas. Angular momentum controls the behavior of orbits. Energy disperses according to predictable rules. The simplicity of these laws contrasts with the complexity of human concerns, offering reassurance that some parts of the universe remain steady regardless of circumstance. This stability provides a background against which all smaller events unfold. Another idea that emerges from studying Andromeda's black hole is the understanding that visibility does not determine importance. The black hole cannot be seen directly, yet it anchors the entire central region. Its presence shapes the motion of stars, the distribution of clusters, and the long-term evolution of the galaxy. Without it, Andromeda would not look the way it does. This concept challenges the tendency to value only what is clearly visible or easily measured. Many important influences, whether in physics, relationships, ecosystems, or societies, operate quietly in the background. Recognizing that unseen forces shape outcomes encourages a more nuanced perspective on how change occurs. At a deeper level, the black hole's ongoing presence emphasizes the longevity of cosmic structures compared to human eras. Civilizations rise and decline in brief periods relative to the age of galaxies. Languages form and transform in centuries. Technologies come and go in decades. Meanwhile, the black hole remains, shaping the core of Andromeda with quiet persistence. This contrast can create a sense of smallness, but it can also provide comfort. The universe does not react to human actions with sudden shifts. It remains steady, offering a consistent backdrop that has existed long before humanity appeared and will continue long after. This constancy offers a form of grounding that helps put rapid change in perspective. Yet, studying something so distant also highlights the remarkable human capacity to reach beyond immediate surroundings. Despite the enormous distance, astronomers have mapped the structure of Andromeda's core, estimated the mass of the black hole, tracked the motion of swirling stars, and predicted how the galaxy will behave billions of years into the future. These achievements illustrate the ability of human curiosity to overcome physical limitations. The tools used today, telescopes, spectrographs, simulations, extend perception far beyond the senses. Understanding a distant black hole demonstrates how far human capability has grown and how it continues to expand. The calmness of Andromeda's core invites a slower form of thinking. Instead of focusing on dramatic events, the region encourages attention to steady processes, long-term patterns, and subtle interactions. This way of thinking can be difficult in a fast-paced world where quick results are often valued more highly than long-term understanding. But the universe rewards patience. The behaviors that reveal the black hole's presence unfold slowly. The patterns that define the core take time to interpret. The clarity that emerges does so gradually, shaped by decades of observation. This approach mirrors any situation in which careful attention and extended reflection yield deeper insight. The upcoming merger between the Milky Way and Andromeda adds a final layer to the lessons drawn from this distant darkness. Even though the black hole appears calm today, its environment will change dramatically in the future. Gas will flow inward, stars will shift, activity will increase. None of this will happen quickly. Instead, the changes will unfold over millions of years. This long timeline underscores how temporary the current state of the universe is. Everything seen today is part of a larger process. Galaxies grow, collide, and reform. Stars are born and destroyed. Black holes expand and rest. The slow unfolding of cosmic events mirrors the slow unfolding of understanding. Nothing in the universe remains fixed indefinitely. Thinking through these ideas reveals why studying a distant black hole becomes a lesson in perspective. It clarifies the scale of human life compared to cosmic time. It emphasizes the value of patience and curiosity. It highlights how unseen forces shape visible outcomes. It shows that calmness can coexist with enormous power. It illustrates the necessity of accepting boundaries while still pursuing deeper insight. And all of this emerges not from dramatic observations, but from quiet details gathered over decades. Saying farewell in a journey like this doesn't mean ending anything sharply. It feels more like easing away from a long conversation, one that has unfolded slowly, patiently, with details drifting into place one at a time. After spending so much time near the quiet heart of Andromeda, stepping back toward a wider view invites a gentle shift in focus. The galaxy still hangs there, stretched across the night in pale light, almost too faint for the eye to notice. Nothing about its shape changes because someone chooses to look away. It simply continues existing as it always has, holding its secrets calmly. A farewell beneath that faint glow is less about leaving the subject and more about recognizing that the story continues long after the last words settle. Taking this slow step back begins by remembering how small our vantage point is. From here on Earth, Andromeda appears as a smudge in the sky. Most people pass beneath it without knowing it is there. Even those who do notice it often see nothing more than a faint streak, a soft hint of something larger. Yet behind that soft smear lies a galaxy filled with hundreds of billions of stars, each one following its own path. Hidden at the center sits the enormous black hole, quiet but powerful, shaping the region without announcing itself. Thinking about the distance between that quiet center and the faint blur visible in the sky helps create a sense of scale that remains difficult to grasp even after spending so much time discussing it. Moving through this farewell, the mind drifts naturally back to the beginning, to the moment when Andromeda was just a distant subject, something chosen for exploration rather than something deeply familiar. Over the course of this long journey, the pieces of Andromeda's structure have unfolded gradually. The bulge, the black hole, the star clusters, the swirling motions, the quiet environment, the future collision with the Milky Way. All of these elements have formed a picture that feels more real now than it did at the start. Yet Andromeda itself hasn't changed. The understanding that grew came from looking closely, from taking the time to examine how something so distant influences the stars around it. The galaxy simply existed while the understanding developed. Returning attention to the core for a moment brings back the image of the quiet black hole sitting at the center of everything. It continues shaping the orbits of stars, guiding clusters, and maintaining the structure of the bulge. Its presence doesn't rely on being seen. It influences the region through gravity alone. The stability of that influence extends beyond any human timeline, remaining steady while civilizations rise and fall. The black hole will be there long after any words written about it fade into obscurity. This thought doesn't create distance. Instead, it creates a form of connection, one grounded in the recognition that understanding something does not require being close to it. Observing it from afar is enough. Stepping further back draws attention to the swirling motions of the stars near the core. Their orbits, shaped by the combined mass of the bulge and the black hole, continue without interruption. These stars do not know they have been used as evidence in human investigations. They continue their paths as they always have. They reveal the presence of the black hole without meaning to. They serve as markers in a larger understanding. Recognizing this natural cooperation between observation and motion adds a deeper sense of quiet to the farewell. The universe does not act with intention, yet its patterns create meaning when humans choose to interpret them. Looking outward from the core, The bulge comes back into view, along with the dense fields of stars that fill the central region. Each of those stars contributes to the brightness that reaches Earth after traveling across the void. This light is dim when it arrives, but the faint glow carries the history of the galaxy with it. The shapes of the orbits, the distribution of material, the motions of clusters, all of it contributes to the light that people see when they look up at the sky. The idea that a faint glow in the night contains the combined light of billions of stars can feel overwhelming. Yet it also creates a sense of calm. The glow is soft because the distance is large, not because the galaxy lacks brilliance. Continuing the gradual step outward brings the disk of Andromeda into focus. The spiral arms stretch across space, filled with regions of star formation and clouds of gas. These structures trace the history of the galaxy's rotation. The arms have been shaped by density waves and gravitational interactions that unfolded over incredibly long timescales. Even after discussing the central black hole at length, the spiral arms remain just as important in defining the galaxy's appearance. They expand the context, showing how the central region fits into a larger whole. The arms, like the core, exist independently of observation. They continue their slow revolution regardless of how often people discuss them. Reflecting on the impending merger between Andromeda and the Milky Way adds another dimension to this farewell. The galaxies are moving toward one another, slowly closing the distance that once felt immeasurable. Eventually, they will interact in ways that reshape both systems. Thinking about this future creates a feeling that the story remains open. The merger has not happened yet. It will not happen soon on human timescales, but the knowledge that it lies ahead influences how Andromeda is perceived today. The galaxy is not static. It is part of an ongoing process that will lead to a new structure in the distant future. This long-term view softens the farewell because it emphasizes continuity rather than closure. Turning the gaze back toward Earth for a moment helps anchor the experience. Whether someone stands in a quiet yard, on a balcony, or beneath a sky touched by city light, the faint glow of Andromeda remains overhead. That glow is subtle enough that many will never notice it, yet it hangs there all the same, unchanged by the presence or absence of observers. This constancy provides a stable backdrop against which smaller, more immediate experiences unfold. The galaxy exists regardless of personal circumstances. Its slow movement across the night sky provides a reminder of the larger universe beyond daily concerns. The farewell also includes an appreciation for the tools and methods that made the entire exploration possible. Telescopes, spectrographs, simulations, and long-term observations allowed humans to uncover details about a galaxy that lies far beyond physical reach. These tools extend perception, granting access to places that would otherwise remain unseen. Recognizing the role of technology in understanding Andromeda helps highlight how curiosity drives innovation. Without these tools, the black hole at the center of Andromeda would remain unknown. With them, the structure of the galaxy becomes clearer. The farewell becomes a nod to the human drive to explore, to seek knowledge, even when the subject lies far outside the range of the senses. Moving the focus outward again reveals the local group, the collection of galaxies that includes the Milky Way, Andromeda, and dozens of smaller systems. This context places Andromeda within a larger neighborhood. The galaxy does not exist in isolation. Its interactions with other galaxies have shaped its past and will shape its future. Seeing Andromeda as part of a network expands the farewell beyond a single galaxy. It acknowledges that everything in the universe is connected through gravity, motion, and shared history. Even the faint glow seen from Earth represents only a small part of a vast cosmic structure. Thinking about the scale of the local group reinforces the idea that the universe is filled with objects that are both incredibly distant and deeply influential. Each galaxy contains its own history, shaped by internal forces and external interactions. Andromeda's quiet black hole, swirling stars, star clusters, and spiral arms contribute to a larger story that includes the Milky Way and numerous smaller galaxies. The farewell becomes a recognition that understanding one galaxy adds to understanding the universe as a whole. It is not an isolated subject, but part of a broader pattern. The next step in this gradual transition involves revisiting the emotions that can accompany the study of something so distant. For some, the vastness creates a sense of insignificance. For others, it inspires curiosity. The scale of Andromeda does not change depending on the reaction it evokes. The response comes from within, shaped by personal perspective. But spending time exploring the galaxy's core, its quiet black hole, its stable clusters, and its future merger tends to soften the feeling of distance. The galaxy becomes more familiar. That familiarity does not reduce the wonder, but instead makes the subject easier to appreciate. This deepening connection contributes to the farewell, making it feel less like stepping away and more like taking a slow breath after a long conversation. As the farewell continues unfolding, the mind returns to the details that gave Andromeda its character. The quiet black hole that sits at the center of everything remains one of the most striking features. Its calmness challenges assumptions about power. Its presence shapes the entire structure. Its future activity will depend on the merger. The black hole teaches patience, perspective, and the value of indirect observation. These lessons linger even as attention shifts elsewhere. They remain part of the understanding built throughout the journey. Stepping farther back brings the whole galaxy into view once more. Dark lanes of dust, clusters of bright stars, elongated arms, and a glowing core all blend into a single structure that drifts across the night. The faintness of its light does not reflect its size, but its distance. This recognition adds softness to the farewell. The galaxy stays luminous in its own space, even if it appears dim from here. Its glow offers a reminder of the vastness between galaxies and the persistence of light across that distance. The final part of this farewell involves accepting that Andromeda will remain in the night sky long after the discussion ends. Its faint glow will continue to cross the darkness, reaching anyone who looks up with patience. The details uncovered during the journey remain true regardless of whether they are remembered or forgotten. The galaxy keeps moving toward the Milky Way, its black hole keeps resting quietly, its stars keep orbiting, its history keeps unfolding across time. Nothing about its existence depends on the presence of an observer or the act of describing it. With this understanding settling gently into place, the farewell beneath Andromeda's faint glow becomes less about leaving and more about allowing the subject to remain where it is, continuing its long journey through space while the observer relaxes back into their own world. Nothing ends. The galaxy continues drifting. The story remains open, waiting quietly for anyone who chooses to look again.